Welcome, everyone, to the joint AIMI and IBIIS retreat. My name is Kurt Langlotz, Director of the AIMI Center, and also during Sandy's sabbatical, the Interim Director of IBIIS. But as you can see, Sandy's not going to be a stranger. He'll be here on Zoom with us, at least for some of the time. Appreciate that, Sandy. Thank you. And of course, IBIIS and AIMI are natural partners. AIMI focused on AI and medical imaging, medicine and imaging really broadly. But we started and are located still within the Department of Radiology, even though our focus is broader. And certainly any radiologist who would be participating in AIMI activities would likely to be affiliated with IBIIS or perhaps have an appointment within IBIIS. So again, natural that the two of us would hold our retreats together, and happy to see all of you here today. So thanks for being with us. We have a great meeting planned. I just want to call out two items that are happening today that I think are exciting. One, a popular session from last year was our affiliates introduction, industry affiliates introductions. We'll be having that a little later today around 2:30. We have great relationships with our industry partners, and I think you'll enjoy it again this year. And the other session is our career transitions panel, which is happening later today. This was a session that was entirely conceived and driven by our trainees. It was an idea that they really felt was important for all of the trainees to hear and see. And I'm really looking forward to that. So, and lots and lots of other things. Of course, our popular poster session to end the day tomorrow. And of course, the fact that we get to be in person together tomorrow is going to be very exciting. So I just want to thank everyone who organized the meeting, including our organizing committee, which was comprised of trainees and led by Kristen Yom, who's serving as our faculty lead for this year's retreat. I'm really looking forward to the day. And so at this point, I'll turn it over to Kristen to get us started. Thanks, everyone.
Thank you, Kurt. Hi, everyone. Super thrilled to have 2021 IBIIS AIMI hybrid retreat and really have this chance to bring everyone together, our members, students, faculty, staff from IBIIS and AIMI, as well as our industry affiliates to really think about research, learn from each other, and also socialize. I think Kurt already mentioned, but I remember when we, sort of IBIIS was established back in 2008. And with a vision of really combining quantitative image analytics, visualization, automation of software tools to more precisely tackle diseases and evaluate therapy efficacy, as well as now we see natural synergy with more recent establishment of our Stanford AIMI Center to really harness advances in AI and really bring about innovations in how we practice modern medicine. And so we're going to kick off today with an exciting agenda. And let me see if I have it. I think I have, there we go. I think I have it here. Sorry, guys. Can you see? Here we go. So this was our pre-COVID, right before, I think this is 2019. We had our virtual meeting last year and our Center for AIMI Center. And so this is our agenda today. We're going to kick off with keynote talk from Professor Ifros from UC Berkeley at 1:15. We will then have a fireside chat moderated by Professors Chaudhry and Rusu between 1:15 and 2:15. And we'll have shortly thereafter a break and also a group Zoom photo session. And then after that, we'll meet our industry affiliates at 2:30. Then we move on to the panel discussion on the topic of career transitions between 3:15 and 4:15, and we will adjourn sometime early, in the late afternoon, I guess. And so at this time, let me see, and that's tomorrow. At this time, it's a privilege to introduce everyone to our keynote speaker. Dr. Ifros is Professor of Electrical Engineering and Computer Science at UC Berkeley, a member of the Bayer Lab. Prior to that, he was 9 years on the faculty of Carnegie Mellon University and also been affiliated with École Normale Supérieure, INRIA, and University of Oxford. His research is in the area of computer vision and computer graphics, especially at the intersection of the two. He is particularly interested in using data-driven techniques to tackle problems where large quantities of unlabeled visual data are readily available. Dr. Ifros received his PhD in 2003 from UC Berkeley. He is a recipient of many, many awards, the Sloan Fellowship, the Guggenheim Fellowship, the Okawa Grant, SIGGRAPH Significant New Researcher Award, 3 PAMI TC Helmholtz Test of Time Prizes, the ACM Prize in Computing, and Diane McIntyre Award for Excellence in Teaching Computer Science. And I'd like to welcome Professor Ifros, and at this time also for our audience members to submit their questions into chat so we can integrate them into our fireside chat discussion. Thank you. Welcome, Professor Ifros.
Thank you very much. Let's see, I need to, okay, yes, I got the slides.
Yes, we can see them. Thank you.
Okay, I think then I am ready to go. Should I start now?
Yes. All
right. Well, thank you very much for a kind invitation, and I'm sorry I can't be there in person, but it sounds like you guys are having an in-person day. We on our side of the bay have also been starting to do some in-person stuff. We just had a workshop on Friday, and let me tell you, it's wonderful. It's so nice to get away from Zoom, but well, here I am. So I am going to give a kind of a general talk on self-supervision, something that we have been working in my lab for a number of years. But if there is some points that people want to ask during the talk, this is perfectly fine, and it's fine if I don't get through all of it. I can skim at the end. Since I don't quite understand the type of things that you guys might be interested in, please do stop me, and if something is unclear, or we can talk about this later on in the question answer. Okay, so let's start with what is self-supervised learning. Okay, this is a term that kind of re-emerged. It actually existed in since at least the 90s, if not earlier, but it has re-emerged that partially due to my lab's work. We really like this term, so we kind of dragged it back from history. It doesn't really have a very good definition. Here is my definition, which I like, which is self-supervised learning is using the tools of supervised learning, but with the raw data instead of human-provided labels. Okay, so unsupervised learning generally, I think of clustering and things like this, right? Supervised learning is different classifiers and things like this. And self-supervised learning is using those tools of supervised learning, like classification, but without these human-provided labels. So somehow getting the data to supervise itself. So this is kind of a beautiful, beautiful story. Before I begin, maybe, why don't we think about why use self-supervision, right? What's the reason for using self-supervision? And kind of the classic answer that I hear a lot is, well, self-supervision is great because, labels are expensive, right? So instead of clicking on lots and lots and lots of images over and over and over again, wouldn't it be great if we didn't have to do that? If we just had the data supervise itself. So this is a common answer, and there is some truth to that answer, but it's not my favorite answer. And the reason is that I think that if for many tasks, supervised learning, classic supervised learning, actually probably is a much better thing to do than self-supervised learning. And those criteria, to me is the following. If your training task and your training data distribution are the same as your test task and test distribution, classic supervised learning is almost always preferable. Okay, so if you're in a scenario when you know exactly what you want the computer to do at test time, and that is what you can provide to the computer at training time, then actually it's worth just trying to get lots of money and just label your data. It's probably the best thing that you can do. Here is a couple of examples. So one is from self-driving cars. This is something that I thought actually, self-supervised learning might be useful. But then talking to my friends in those areas, they say, well, we don't really need to do it because, as for example, Tesla, Andrei Karpathy somewhere said that, we use our drivers as the source of supervision, and we just collect all this data. And even if we need to do some labeling, that's not so bad. And so here's my kind of back of the envelope calculation. The distribution of all the roads in the world, you'd think it's actually very huge, but it's not really that bad because, there is about 8 billion people right now living on Earth, right? But there's only 24 million kilometers of road on Earth. So basically, that means that you get 122 people per kilometer of road on Earth. And so then asking one of those 122 people to label a 1 kilometer of road near their home, or to drive around on their car and kind of get the car to label it for you, is actually not that crazy of an ask, right? This is not really that bad. And the nice thing is that what you get is kind of what you need from that labeling. It's not like you're hoping that somehow the labeling that you have is will it be aligned with what you actually want or not? Well, no, because you want to have, you want to drive safely at training time and you want to drive safely at test time. So, there is a very nice alignment of data as well as task. Another example that may be closer to what you folks are thinking about is CT scans. You can't imagine how many times people from medical imaging and doctors contact me because our lab has been doing a lot of work on GANs, and they say, oh, can we use your GANs to generate more training data for our algorithms? And to me, that always sounded very strange, because getting GANs to generate good training data is extremely hard, and it will never be as good as real training data, right? So it's especially in something as critical as health, you think that you really want high quality data, and the thing is, like, you do have quite high quality data, right? There's, I don't know, tens of millions of CT scans available in the world with health outcomes, right? Now they're all distributed across the world, but they exist. And so it seems to me that in these kind of cases, it's actually much better off just going and trying to get this data and putting it all together. And of course, it's a lot of work, but the quality of the models that you get from this real data will almost always be better than whatever we can do with self-supervised learning. Okay, so with this caveat, then why self-supervision? So for me, I have three answers to this question, and here they are. Answer number one is to get away from semantic categories. Answer number two is to get away from fixed data sets. And answer number three, to get away from fixed objectives. Okay, so I'll spend most of my time on one, do a little bit on 2, and maybe I'll touch on 3 if we have time, but maybe not. Okay. So getting away from semantic categories. So why is that important? Well, semantic categories are actually problematic. Okay, and here's a couple of examples. So here is an example from kind of a standard object data sets that everyone knows and loves, you know, ImageNet or Places. So these are examples from the category chair. Okay, and if you look at them, you realize how amazingly varied those examples of the category chair are. And you also realize that the reason that we humans can tell that all of them are chairs is really because we have a lot of experience with these things as affordances, as something that we interact with, right? So the reason we know this is a chair is because kind of we are aware of, you know, squeezing our own bottoms into things and then, you know, putting, you know, taking a sitting posture that way. But a computer that has never seen anyone, you know, sit down, doesn't have a bottom of its own, just looking at these example images, that just not enough information to realize that there is something in common here, because what's in common is not really in appearance, but more in the functional kind of a use of these different examples. So you're asking the computer to find something in common between things which don't really have that much in common. Another example is these two pictures both have a labeled city. Okay, so this is downtown Pittsburgh, where I spend a lot of time, and this is center of Paris, where I also spend a lot of time. And let me tell you, the fact that both of them are, by some fluke of the English language, named with the same English noun, city, that is actually not helpful at all for trying to recognize them, because if you look at them, there's really nothing. There's not a single pixel in common between these two things. Okay, you can say, well, you know, both of them have buildings, right? But look at the buildings. The buildings are completely different. You wouldn't know that both of them are buildings unless kind of you walked into them and kind of interacted with them yourself. And you can say, well, wait a minute, but you know, the buildings, they all have windows. But again, look at this. The windows here and the windows here, they don't look like each other at all. And it's like this all over the place. It's really, these two have very little in common visual. Their commonality is functional, not visual. But again, a computer doesn't ever experience cities except for these images. And of course, then the computer is really kind of at a loss. So we're really, with labels like these, we're basically setting up our systems to fail, because really the best thing that a computer would do in this kind of case is what I did when I was an undergrad, and I didn't really go to lectures. I didn't really understand the material. So I would just cram for the exam. I just trying to memorize typical questions and typical answers, right? And that's exactly what a lot of the times the classifiers are doing. They say, well, I have no idea how these two are related, so I'm just going to try to remember this, and then hopefully at test time I'll get something simple, okay? Which is not really what we want, okay? And so the problem really goes all the way back to the ancient Greeks, right? Kind of the classical view of categories dates back to Plato and Aristotle, and the idea was that a category is defined by a list of properties that are shared by all elements. Category membership is binary, either you're a city or you're not a city, and every member of a category is equal. Okay, so this was kind of the Platonic story for categories that actually most of us still kind of carry on with in our brain, 2,000 years later, even though humans actually in actual experience and trying to understand the world, humans don't appear to do this at all. even though we think we do this. We don't actually seem to be doing this. Wittgenstein and following that, Eleanor Roche here at Berkeley had a really kind of nice rebuttal in the 20th century about why these are not really what we humans do. So we don't really rely on these abstract definitions or list of shared properties. Wittgenstein's classic example was, can you define a list of properties shared by all games? Okay, and the answer is no. There is no. It's impossible to do that. There's all the games could be so varied. There is not a single thing that's in common between all of them. And other kind of Platonic ideas like typical binary membership, right? That either you are a bird or you're not a bird. Well, it's not quite so simple because chicken is a bird, right? But when you think of a bird, you really think of eagles and sparrows and not really chickens. So there seems to be some kind of inequality within categories. There is also weird language dependence, right? So for example, in my native Russian, there is not a single word for chair. We have 3 words: stool, kreslo, and tabretka. And so that kind of suggests that if I'm writing a object detector in Russian, then somehow I get a different result than if I were coding it up in America, which doesn't make sense. And so in the kind of middle 20th century, people started to feel that instead of this top-down kind of categorization kind of imposed from this Platonic ideals, a better model might be a bottom-up association, okay? And so Eleanor Roche proposed the prototype theory, and then that followed on exemplar theory. And I like the way Moshe Bar talks about this in his papers. He says, ask not what is it, ask what is it like. So the idea is, instead of having this ideal Platonic chair and then listing everything that fits that Platonic chair, the idea is to start from the bottom, start from the data itself, and see if you can kind of cluster and connect it together and associate different examples with each other, and hopefully you'll get something emerging from the bottom up. This is something that I've been thinking about for a very long time. This is our work from a decade ago, where we thought, instead of thinking about kind of standard classification, for example, classify one class from another class or one class from everything else, and back then SVMs were all exciting and hot, so we were using SVMs, and that argument is that it might be that really there might be nothing in common between your positive category. And so what we propose to do is to instead do every single instance, classify that against everything else in the universe. And then we have a kind of an ensemble of these one instance against everything. And we found that basically worked as well as this category classifier. But in addition to that, you are always also able to get other extra nice things, like you get correspondence basically for free, because you find things that are very similar to this particular thing. So it was kind of a nice way to think about categorization without the idea of categories. And then we also used it for image retrieval, where it's kind of the same kind of idea. You take an image, and then when you want to find the closest set of images, you again just basically train a classifier from that training image, from this input image, to everything else in your data set. And it turns out that the closest kind of the hardest negatives that your classifier finds are good matches for this image. Okay. So this was a decade ago, and then when neural networks came about, we tried really hard to update it to convolutional neural networks, and nothing really worked for us. So we kind of gave up. But another group, Desavitsky and colleagues, they actually did manage to make it work with CNNs, and this is their work of exemplar CNNs. And basically the idea was to, again, use a single example and then train a neural network to classify that single instance against everything else in the data set. The only thing that they made, the reason why our things didn't work and theirs did, is that instead of just having a single instance, they added a bunch of other positive instances, which were basically just variations of that instance, what's we call now data augmentation. So basically we take an the instance and then we flip it, change the color, blah, 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 but it's basically the same data, okay? But there's just now more of that. And this was the positive set, and then everything else was the negative set, and then it worked very well. And fast forward to more or less now, and now this is a very big area, this kind of similarity learning, the latest is contrastive learning, but basically it's all the same idea, right? We give up on the whole category story and we say, okay, let's have a single instance. We create a few positives from that single instance by doing data augmentation. And then we try to separate it, push it as far away from other instances as we can. And that produces a good problem, self-supervised learning problem that we can then create good features. So, and again, why is it like it's been getting better and better? You can see lots and lots of works on this. And so, part of the reason that it's been successful is, we definitely have genuine improvements in the techniques. For example, the contrastive learning was definitely better than kind of the Siamese networks that we used before. But I think maybe more importantly, we're getting better and better at learning how to generate this data augmentation, how to create these multiple positive instances. So again, kind of data augmentation. So let's say you have your image, and then you want to create multiple versions of this input image. And what you do is you basically just randomly perturb this image with various perturbations. Maybe change the color, maybe do some cropping, maybe flip the image left, right, maybe blur, etc., etc. There's a whole list of things that one can do, okay? And then you just add it to your positive set, okay? Well, unfortunately, there is no free lunch, because as we have been getting better and better at this data augmentation, we begin to realize that itself is a kind of a form of supervision. The choice of which augmentations to use here is proposed by the programmer. So there is actually a human figuring out what would be good augmentation. And what we find in this paper is that actually the choice of augmentation is extremely important for doing well, and doing well on different tasks. You need different augmentations. So, for example, if your goal is to do normal kind of categorization, like ImageNet categorization, then augmenting with color and augmenting with different textures, that is very helpful. But rotating the image actually turns out not to be very helpful, because an upside down elephant is that will never happen in practice, and so you're actually going to make it worse for your classifier. Okay. On the other hand, if your goal is fine-grained categorization, for example, you want to tell apart different types of birds, well, then actually none of those augmentations are good, because if you change the color of a bird, it actually could be a different bird. If you rotate the bird, the same thing. Well, upside down birds you'd never see, and then texture of the bird also is very useful. On the other hand, for something like fine-grained categorization for flowers, the rotation is perfectly fine, because flowers are rotationally symmetric. Okay, and so basically, it sounds like we were hoping to get away from this yoke of the human labeler But now we are under the yoke of the human data augmentation inventor. And again, we're forced to, to hack what is a good augmentation. And so what we were thinking about trying to do in our group is to try to see if we can get try to not use data augmentation, okay, or rather to somehow create these data augmented views on their own without using human. Okay. Now, of course, the question is, but how do you get the supervisory signal? Where do you get the supervision? And for one of the projects, we thought that the very nice and natural supervision signal is time. Okay. Let me quote from one of my favorite authors, Jorge Luis Borges, in this short story about a man on the spectrum. It irritated him that a dog at 3:14 in the afternoon seen in profile should be indicated by the same noun as the dog at 3:15 seen frontally, right? So for this gentleman, he could not figure out that this and these dogs are actually the same dog, okay? But most of us can figure out that it's the same dog. Why? Because the time binds them together, because we know that it's very, very unlikely that somehow dogs were switched and that this dog is different from this dog, right? We know that like time preserves identity. And so that made us think that time might be a very good supervision for what should be the same and what should be different. There is also an example, a very, very nice paper by Wood to show that chicks that are just born chicks, temporal consistency turns out to be very important to them. And if you don't get, if you only see input that's not temporally consistent, the chicks have major problems with their visual system. So nice motivation from there. So basically the idea is using video as a source of data augmentation. So basically saying that there is some this and that and those should all be considered one thing, should all be kind of on the positive side. Okay. And then of course you can kind of reason with common fate and talk about segmentation and grouping as well using that motivation. Okay. And so people have had this idea for a while, trying to use temporal coherence across frames or trying to mine correspondences, but this was also kind of a little bit of hodgepodge approach. And so what we proposed last NeurIPS was to see if we can do it all in one kind of nice framework using a random walk on a graph. And so here I'll just give you a little bit of a taste of what the idea. So imagine that we, for once, let's say that we do have supervision, that some human came and said that this patch matches with this patch, okay? That these two should be together, they should be positive, okay? Well, this is all fine. We have this kind of nice correspondence, but because it's a video, we know that this patch should get back to here, but then it's in the middle, in a frame in the middle, it should go through somewhere reasonable. Okay, and so we find a patch, the most likely patch through which it can go through, and we realize that it's probably going to be this one. Okay, and so now we were given that these two patches are the same patch by a human. But now we can also augment it with this frame and say, okay, well, if these two are the same, then it must be this one, because where else would it go through? Okay. And so now we kind of added one more extra latent view to our data augmentation. Okay. So this is good, but we can do better. And here's how we can do better. Now we can get rid of this human supervision altogether by making a palindrome out of our video. So our video is 1, 2, 3 frames. What we can do is we can flip the video backwards and get it back to where we started. Okay, so flip the arrow of time and say frame 1, frame 2, frame 3, and then frame 2, frame 1. And now we can try to find a kind of a cycle through this video, starting and ending at the same place. Okay, but then in the middle, it needs to do something reasonable. It needs to find a good path. So here it will basically try to find what is a good correspondence. And then eventually, kind of the idea is that we're going to walk through this graph and we will find what is the most likely path. And now those things that our path goes through, they all automatically become our positives. And then we are able to create a set of positives, kind of generate data augmentation automatically without using any hacks and without any human supervision. Okay, so the idea is we make this palindrome graph. We take our video, we turn it into a graph from t to t plus k and back down to t. Okay, and now we basically, we start with some node here, and we are going to walk on this graph with a random walk, and we're going to steer this random walk such that it ends up at this green node right here. And the green node is just exactly the same as the starting node, right? Because it's a palindrome, we set it up so that where we start, we should edit the same thing. So basically, we want to find a feature representation that will bring us from here, walking down the graph, to the green node. So the green is our positive. All the reds are our negatives. We don't want to end up at the reds. And also all of the things that it can go through in the middle are also our positives. Okay, and so now we have set up a nice framework where we can get a setup where we can have the positives, we can have the negatives, and we don't have any human supervision in whatsoever. Okay, so I'm going to skip the details of this and just show you that we can use this now for label propagation in video. So this is a competition. This is previous state of the art result, and this is our result. You can see that it's sticking much better to the people and kind of gets less confused when you're and there is also, we have numbers to show that we are actually we're not only better than other self-supervised methods, but we are also better than methods that are supervised by human labels like ImageNet and stuff like this. Okay. Another thing that I wanted to quickly show is another way to try to get supervision without kind of getting humans, and that is to use GANs as supervisory signals. And now I said that it was kind of it's a dangerous thing because ideally you would just use more data, but sometimes there isn't really more data, especially if you want to find correspondences. It's very hard to get labeled data for correspondences. And so the idea is we were very much inspired by this very, very old paper from Eric Learned Miller from 15 years ago called congealing. And the idea of that paper was to take a whole bunch of data set, and it's a nice word, congeal it together to get into correspondence with each other. So these are different digits 0 from AIMI's data set. And the idea is to basically try to warp every single one of these zeros towards a common mean. And as you're warping it towards a common mean, the mean itself is also getting sharper and sharper, while all of your constituent data points are also getting sharper. Okay, so it's a very nice kind of a precursor to self-supervised methods, and it works really nice for things like binary data. Unfortunately, it didn't really work well for real data. When it worked really well, but it didn't really work on complicated data. And so that method was kind of forgotten, but I always thought it would be kind of nice to revisit it using modern techniques. And now we do have modern techniques. We have GANs. And the nice thing about GANs is that GANs kind of, if you look at like these, GAN producing, trained on cats, there is definitely kind of, GANs do know something about correspondence. You can see that those cats that it's producing, they're, as we walk through the latent space, they're not jumping around. There is definitely some kind of smoothness. So it's almost like a video, right, that the GANs are generating. And we're thinking, can we use this again as a way as a learning signal? Okay. And so this is our work that we're about to post on archive in the next week or two. We should have it up. We call it GAN supervised dense visual alignment. And basically the idea is as follows. We're going to generate our training signal that we're going to train from by using a GAN, but changing around some of the parameters, the style parameters of a GAN, so that we can have pairs of data that are similar, but not quite the same, okay? And now that we have these pairs, we can train a transformer. This is a spatial transformer, not the other kind of transformer. Train a spatial transformer to find a correspondence, a vector field that to correspond from this to this, okay? And once we have those correspondences, now we can basically learn how to make a correspondence between all of the data that we have. And then we can basically do congealing, we call it gangealing. And so here's an example of what we can do then. We can basically compute an average, a mean, a congealed image of kind of all the cats being aligned or all the human faces being aligned, okay? This kind of like Easter Island kind of faces. Or we can do cars, all the cars being aligned. And here is the horses being aligned, okay? And so here are things that we can do as it's training. You can see that you get a kind of the average image, the mean image becomes much better. And now you can propagate all the any kind of annotations you have in one face or one cat. You can use your average to propagate it to all the other cats that you have. So this is kind of a way to get yourself some correspondences. So here is the same thing for birds. Okay, and now this is a correspondence. There we go, and we can propagate them back. And this is the same thing for humans. Get your average is getting better and better and better. And then we can propagate it, and then we can go back to it. Okay, and then we can even do it on YouTube videos. It's kind of it does break down if there's too much zoom, but it's surprisingly robust given that it's basically one frame at a time. You can see that it's yeah. So there you go. It's not too bad. Not too bad. Okay. And we have some kind of transfer of key points results that seem to be pretty cool. And one thing that I'm very interested in is to try this on some medical data, but like we looked around and it all looks very complicated. But if somebody is interested in trying it on medical data, we would love to help you out and see how it works. And we can also do various cute things like propagate propagate other cute things to the yeah. And then we can add things on your cars and add mustaches and things like this. Okay, so I'm thinking I think maybe I'm out of time. Is that right? When do you want me to end?
We have about 8 more minutes.
Okay. So let me just give you just a quick feel, or I think maybe the first one was really the most relevant for you guys, but let me give you just a little taste of the other two. So getting away from fixed data sets. This I'm not actually completely sure is very relevant to you guys, but I've been kind of worried about having data sets that are fixed forever, right? And part of it comes from the real world motivation. Biological agents never see the same data twice, right? So, it's always like you see a new piece of data, first it's the test data, right? You encounter for the first time, and then if you survive, then you get to train on it. If you don't survive, too bad, right? But then you never see this thing ever again, right? That thing, it basically, once you saw it, that's it. You'll never see it again. Next time it will be something, you know, it might be a tiger, but it will be a different tiger, not exactly the same tiger. And so here, when we have like the standard data set, like ImageNet, and we just train on the same, you know, the same amount of data over and over and over again, it's basically just begging to memorize and discourages generalization. And this actually might also explain why data augmentation is such a big help, because data augmentation kind of is random, and it's randomized at you know, at every time you see a data, it's slightly different because you're adding some random augmentation. And so this might be the reason why it works so well, is because it kind of gets you to not see exactly the same data. Okay, but the thing is that the only reason that people use fixed data set is the annotation expense, right? It's because once you annotate a data, it's very expensive, so you just want to use it more than once. But with self-supervision, we don't have that excuse anymore, right? If we don't need humans to annotate the data, there is absolutely no reason to ever see the same data twice, because, you know, there is huge amounts of data, and if you don't need to label it, you should never look at the same data more than once, right? You should always kind of push your algorithm to see new data, right? And it's kind of like this continual kind of online learning story. It kind of makes a lot of sense if you think about it. It's from the kind of a train and val split. So you have your training set and you have your validation set, right? And instead of using all of your thing for training, it turns out to be better to train on some amount and then use the rest for validation. Well, the same thing for kind of in a continuous case, where you train a training set, and then you have the next thing as your validation, and then once you validate on that, then you take the next one and the next one, and it makes sense that, especially when your data stream is changing, you know, humans are getting heavier, living longer, you know, the data you collected 30 years ago might actually not be that relevant. So it actually makes sense that you keep training as you're processing your data. And so we have this little work, we call it test time training. And the idea here is to use a data self-supervision as a way to kind of train on the job. And so if you think about this kind of standard testing error, so your testing error is basically the loss function between your output of your classifier and the correct label given parameters under your distribution Q. But the thing is that your new test sample X actually gives you some information about your distribution Q, in case that your distribution Q might be different from what you trained on. Okay. And so the idea of our continual testing error is that the parameters of your classifier could have X, could be a function of X, could be a function of your testing sample. Okay. And so now it's kind of like you have a one sample learning problem, right? So for every sample, you want to kind of learn what's the best classifier for that sample. Of course, you don't have label, but we can have self-supervision. And so the idea is like, this is a very simple kind of instantiation of it. Let's say that you want to classify images. So you give this image and you say, okay, this is a bird. So this is what you train on. But you also, at the same time, you have another self-supervised training loss. And in this case, we are just using the stupid rotation prediction. So we randomly rotate the image four ways, and then we ask it to predict which of the 4 rotations it produced, right? So we basically train it to do both of those tasks, but it's using a shared feature, okay? And now at test time, of course, we don't have any labels that tells you what what label this image is, but we still can produce a label for our self-supervised task, because we can always just randomly rotate an image, and then, you know, the label is how much you have rotated it. So we can still update this network a little bit at test time to see if we can get it to be a little bit more attuned to the test sample that we are looking at, okay? And basically, that's the idea. So the idea is that we are going to fine-tune your network at test time before we classify our test sample, okay? And so here we have an example where, given this image, in the beginning, the network was a little bit confused and it thought that this was a dog. But after doing a little bit of self-supervised training, we saw that basically the elephant becomes more and more confident and the dog less and less confident. So it's kind of adjusted the features so that it realized that it was, after all, an elephant. Okay. And another nice thing about this is that we can think of it as like every single new test example is kind of a start, you know, starting from scratch, a completely new problem, and then we adjust our parameters from scratch, right? Or, and I like this actually more, we can think of it as in an online version, whereas that every new piece of data fine-tunes the model that we are kind of updating. So we don't start from the pristine model all the time, but we just keep fine-tuning. And this way, we can handle smoothly changing distributions, because every new sample adjusts our model a little bit, and so it kind of follows the distribution as the distribution is changing. Okay, and we see that we actually can get quite a bit of an improvement compared to previous methods using this trick. And we also showed this for adapting from a robot trained on in simulation to a robot deployed on a real robot, and you can see that this is the simulation and this is the real robot, and you can see that the real robot is able to do the same task as the simulation, even though, you know, it's much more noisy, and we actually also add some, you know, some cool strobe lighting there to confuse it even more, and it's still able to do this because it's able to do this adaptation. Okay, so I'm not going to talk about the last one because it's also the most heavy, but basically, oops, sorry. But basically the story is to get away from semantic categories. The one way to do it is to use data-driven bottom-up association. To get away from fixed data set, continuous lifelong learning, and to get away from fixed objectives, emergent objectives, which are basically trying to get some kind of arms races and get your adversarially create the new objectives automatically by the algorithm. All right, thank you very much, and I'm happy to answer questions.
Thank you, Professor IBIIS. That was really, really wonderful. I'm sure our audience have a lot of questions. We're going to transition to fireside chat, which will be moderated by Professors Akshay Chowdhury and Mirabella Rusu.
Hi, Dr. Efros, and hello, all the participants to the retreat. That was a very, very fascinating talk. I have a ton of questions, and as Dr. Yom mentioned, I'm sure we all do. As folks are getting ready with their questions, please type them into the chat. And if you do want to speak up, just raise your hand using the reaction button, and then we'll get started. So I don't see anything in the chat as of right now. So maybe I'll ask the first question, and then I'll pass it to my co-moderator, Akshay Chowdhury, also an assistant professor in the IBIIS division. So my question for you is, we know very well that some of these models that we are developing can be biased. Right? And a lot of it comes from the data. Some of it comes also how we set up the problems. How do we go around having issues with propagating bias when we do self-supervision, when we use and augment mainly from a data set that we have?
That's a very good question. Actually, I've been worried about data set bias for a very long time. Before it was cool, we had one of the early papers, we call it unbiased look at data set bias, and our conclusions were maybe somewhat pessimistic, but also kind of just our conclusions were that it's basically, you can't, I don't think there is any way around it. That I think we'll just have to learn to live with bias, mainly because it's impossible to define what does it mean to not have a bias. In fact, there is depending on, for example, let's say you're looking at navigation, and you put a camera on your forehead, and then you record all that data, right? Whether you are a human or a pigeon, your view of your world is going to be completely different, even though it's exactly the same world. The world has not changed at all, but your experience of the world is going to be tremendously different. So which one is correct, right? One is a human bias, the other is a pigeon bias. Which one do we want? Well, it depends, right? It depends on the task. That's why I think the best case scenario is, like I said in the beginning, if you're in a very nice and happy position where your task and your data distribution are the same at training time and at test time, then I think it's going to be biased, but it's kind of exactly the right bias that you want. So, like, if you're treating patients of whatever set of 100 nationalities that come to Stanford Hospital, and you're training on those 100 nationality of patients, if you expect the same distribution of nationality to keep coming in, next year and the year after, you're good to go, right? It's only when things start to change, or only when somehow you realize that the data you trained on does not actually fit with the test data that you will need to use at test time. Having said that, I think a lot of the bias that is in the news and is kind of getting talked about in regards to computer vision is actually label bias, right? When again a human puts some label on an image, and that label is actually not a very good label for this image, right? And in that's kind of one of the reasons I am a big fan of self-supervision, because just getting the human out of that process, at least on the labeling side, is always going to keep you closer to the true data. So that's why I think, I guess in the medical context, instead of labeling with like a name of a disease, which who knows, maybe it's the wrong name, or maybe there is a similar name, or maybe in different countries it's called something else, or maybe it turns out to be a wrong name and it's actually 3 diseases. Instead of doing that, labeling with something that's much more data driven, like treatment outcomes, or like life expectancy, or something that's not going to change over time, is one way to try to get away from some of this bias. So I think the less kind of human there is in your process, the less bias you're going to have. But I don't think you will ever going to get rid of it completely.
Thank you. Very, very nice answer. Akshay, do you want to take it away?
Yeah, absolutely. I have quite a few questions, but I think I'll forego them for all the audience questions that are being posted. And maybe I'll start with a question that was posted in the chat by Kurt Langlotz, who says that CT was used as an example of why self-supervised learning is not necessary because we have so much data. but we actually have very little label data because labeling scans can be expensive. Wouldn't that suggest that self-supervised methods have strong appeal in medical imaging? And maybe I could add an additional part to that question. In the second part of your presentation, you said that self-supervised learning can be appealing when our training data sets are not fixed. With medical imaging, we see that our data sets are quite stationary. There could be temporal shifts, there could be spatial shifts. So I'd be curious as to what your take is on that.
So yeah, I'm very, very confused about kind of I guess I don't understand a lot of the tricks of the medical imaging trade, but it seems to me that you guys actually have a lot of labels for your medical scans, right? Because the medical scans are part of the medical history. So with a scan, there is the standard things like age and gender and whatever, blood pressure and all that stuff, right? And I guess if you just do a little bit more work, you should be able to kind of look at outcomes like life expectancy or whatever, like what is survive, how many years they lived, and things like this, right? I think that this is actually a fantastic amount of data. So, for example, I would imagine that, like, if you have doing, and in this case, maybe like a self-supervised task might be a kind of a cool way. For example, you take your CT scan and you try to predict the age of the patient, right? And then presumably for healthy patients, that predictor is going to work very well, but maybe for an unhealthy patient, it may be predict the age to be older than it actually is, and then you say, okay, something is a little bit off, right? But I think fundamentally, I think there is a lot of labels, and it might be that some of these labels are maybe not exactly the labels that you want at this particular time, like a picture of a lesion somewhere, right? But you do have a lot of data, and I guess it's some work to try to kind of collate it all together and have it available. But I think it's a gold mine of cool data that could be used. And some of it, again, as I mentioned before, some of it might actually be less biased data. Like it's much less biased to have a patient's age than to have some sort of a segmented lesion region which some radiologists labeled where they may or may not be correct or things like this, right? So I think that it's kind of weird to me that whenever I talk to radiologists, their data sets are usually extremely small, like thousands of scans, whereas I presume that one has millions or tens of millions, right, available, and it seems like this is just a lot of gold just sitting there in these on my charts all over the world, just waiting to be used.
Maybe I'll have Kurt respond to that briefly from a clinical perspective, and then we'll move on to a question by Anthony, who had his hand raised.
Mm-hmm.
Yeah, 1,000 is a big data set for us. So you're right, there is a lot of clinical data, but it's got all of the issues with labels. So there's not a perfect correlation between information in the medical record or even the report and the image. So it's actually quite expensive even to generate labels from the other data that we have. So I guess that just, so anyway, I mean, to me, it's a positive message. I think that the techniques that you described today are very much relevant to what we do.
Yeah, I just want to say that, like, a lot of these issues, like, they are totally solvable issues. There are people next door to me, working on databases, like database researchers and computer science departments. Like, they know how. It's not tricky. It's not easy, but it's not like fundamentally hard. It just, somebody needs to get this data and just hook up all of those data sets together. Like, it's like, we know how to do this, and I feel it's kind of sad that because I would love to have access to all of this data too. I would love to work on this. And so, because 1,000 scans, frankly, like for, okay, these scans are larger, so you have more pixels, but like in my field, like when we have only 1,000 data points, we say, okay, that's just not going to work. Like we don't even touch anything with only 1,000 data points, because we know it's not going to train well, right? So I want to encourage you to bug your database people in the Stanford Computer Science Department to just get on it and just fix this, because these are all fixable problems.
What I would like to add is that you can see all of us smiling as you are saying all these things. We all want the same thing. We are all working towards getting all this the scans, and it's not as trivial as we would like it. It's not a problem of storage or database. I think Sandy also mentions it's a privacy issue as well, among others.
Right. No, I understand that part, but there is also solutions for that. There is some really nice work on differential privacy that might be useful. Yeah.
And I do want to go ahead with one question from the audience, from Jean Long, that mentions that, thank you for the wonderful presentation. My question is, it seems like self-supervised learning could save the effort of exhausting annotation. However, it's still based on a limited data set, which we provided. How does it deal with overfitting issues with limited data?
Well, I think that's the argument I'm trying to make, that once you have self-supervision, you should not be limited by the data set. I think once you buy onto the whole self-supervision story, you shouldn't have a data set, right? You should just, patient comes in, you just process that, next patient process that, and just keep it as a kind of an online continual mode, because the whole point of having a data set is because once you label something, you want to keep it around because it was expensive to label, right? But if you have like this pipeline of just always getting new data and not needing to label it, then you don't really need to have a small data set. I think I'm completely agree with you that if you still have the small data set, then self-supervised methods are not going to do much better for you. They might do a little bit better because you can think about this in terms of how much kind of label signal do you have per image. So for example, let's say ImageNet. ImageNet, you have a million images, but then every image has only one label. It's like it's a dog, or it's a car, or it's a cat, etc. Right? So you get like one thing per image. Whereas with self-supervised learning, for example, something that we did was a colorization task. So we take a grayscale image and then we try to predict its color, right? And that you have one label, one color that you predict per pixel. So every image has now, hundreds of thousands of things that you predict instead of a single thing to predict. So you can kind of get a little bit more juice out of your limited data set because you have more, you can generate more of these labels than what a human generates for you. So there's a little bit that you can get that way. But on the other hand, those kind of self-supervised labels might not be as powerful, and they might not be exactly what you're looking for. And so in general, I think small data is always going to be a problem. And it's the first thing to do is to try to get your data bigger, and then life always becomes better.
I think one of the interesting facts that this brings up is there's a requirement to have these generalizable and robust embeddings that we can build up in a self-supervised manner. But this is a nice question that was asked by Belize Gunell in the audience, who's asking about, is there a principal way to pick a pretext task, knowing what is a downstream task of interest that we care about? Is this data set dependent? Do we need an RL policy to figure out the right task, the right data set? How do you think about that?
Great question. And I have no idea. And I don't think anyone has a good idea. we know that it's very relevant, like this example I showed with the contrastive learning, where the type of data augmentation. So like now the different data augmentations in contrastive learning are kind of like the pretext tasks in a classical self-supervision. And we do see that a lot of work is spent just hacking all those data augmentations to kind of connect with the task. So for example, a huge data augmentation, like the data augmentation that really made things work way, way better is cropping. So you take an image and you crop a part of it and you throw it in the bin. But that really works well for a task of image classification. You know, is it a car, or is it a dog, or is it a cat, right? Whereas you basically, you know, you have a cat in the middle or you have a dog in the middle of the image, and so cropping actually helps it out. If your task is detection, like you're trying to find the cat in the image and there are maybe like many different other things, then cropping actually is a really bad idea, and it will make things worse for you. So I think it's a great question. I think right now people just you know, it's art. You know, people just come up with things that they think might be useful, but nobody really knows anything better than this. And you know, this is why we were looking at trying to do self-supervision from a video, because the argument is, well, a video is a whole bunch of real data all strung together with time. Maybe that's going to be useful. But you know, there's pluses and minuses. So I think at this point, everybody's trying. You know, we also try to kind of automatically try to do some meta learning to try to discover the perfect pretext task. Yeah, never worked. So yeah, I think this is open question.
Anthony Gatti still has a question, so we can let him ask in person.
Thank you. So I typed mine out. I was curious when I saw the GAN Geo. The thing that stood out to me was it looks like a lot like image registration.
Exactly, it is.
Okay, so but it's
image registration without any there's no human labels. It's automatic.
So then I definitely think the imaging community would be quite interested in the method applied for image registration. So one of my other questions was, do you think it can be transferred to other data types? So I work with point cloud data or surface meshes of bones, for example. So could we apply it there? Number one. And then the second point is, which I'm worried about the answer based on some of your comments previously, how much data is likely needed to train this type of model?
Right. So meshes, I think, are actually, believe it or not, meshes I think are easier than pixel data in many ways, in terms of complexity. So I think you probably need less mesh data than you need pixel data. So that's a good news. So the basically our method is contingent on training a good GAN. So if you can train a GAN like a style 2 GAN, for example, on your data, which, you know, 10,000 images plus, maybe 1,000 if it's really kind of boring, consistent data, then we can talk. So that, yeah. And by the way, if anyone is interested, try their data, and you guys have, you know, enough of it to train a good GAN, please email me. I'll hook you up with the graduate student who would be eager to work with you to try it, because I think I feel like this could be a very useful tool for folks like you guys. But you know, we don't know anything about this data, so it would be great to work with you guys and make it happen. Yeah, we're very eager. So just email me and I'll set it up.
Sounds great.
But we do need lots of data. Yeah.
Okay. So thank you.
And maybe I know we're a couple of minutes over, but we have one more question by Rohir Vanderslois, who asks that SSL self-supervised learning solves some of the problems with incorrect human annotations, but how can we ultimately evaluate the performance of learned representations? Is there a better alternative than linear evaluation on ImageNet that may have noisy labels too?
Oh my God, you know, the whole linear thing on ImageNet, I'm very ashamed of it, because like this came out from my lab, and we thought we would just do it once because we didn't have enough GPUs to do the proper thing, and then it just kind of took off, and now everybody's doing it. I'm very sorry. It's a very bad evaluation. I completely agree, and I wish that we didn't go down that path. Definitely, the right way to evaluate it is on some sort of a well-defined task, right? And the hope is that for some sort of a task that people actually need, there would be like a nice, either a labeled test set, because labeling test sets is not as bad as labeling training sets, right? Especially if you do it properly, and you have your labels stashed somewhere in an undisclosed location, and like you're only allowed to test on it like once every half a year or something, right? So people don't overfit. So like, this is not, that would be like the gold standard. Some really useful, important task that you can submit your code and like train and test on it, once in every half a year, and then we can see if there is actual progress being made. And that would be a great setup. But this is something that, of course, one needs to really have a good task that is actually universally agreed to be useful. I think one could also have tasks that are kind of self-supervised testing as well, right? So if you can predict something that's not human defined, I think that would be the best. Like, survival rates, like given a scan, is the person still alive 5 years down the road, right? Well, that's a very kind of human. It's not, there is no human labeling involved in that, right? You just need to get the data, and then the patient died or the patient didn't die, right? And that again, to me, sounds like a great evaluation. Again, if we kind of hide it in some closet and only let people test on it like once every half a year, that would be a great thing as well. So I think if your community is willing to kind of come up with this kind of gold standard evaluation, I think that would actually be great for all of us, because I think everybody knows that linearly testing on ImageNet is really, really stupid idea, and we would love to do something more useful and more objective. Yeah.
Point definitely taken about using higher order tasks. But again, I just wanted to thank you, Dr. Efros, for taking the time and for having a great discussion and trying to answer all the questions that we posed. I think it's really inspiring to try to bring together the medical imaging communities with the CS communities to try to figure out the problems that both the communities face, and then hopefully try to find a solution that converges in the middle. So thank you again for the time. So maybe a round of applause virtually in Zoom for that wonderful presentation.
Thank you very much. It was a pleasure.
Thank you, Professor
you.
Efros. So we actually, I want to say one more thing. I thank you so much for showing those videos as a way, kind of like over time, right? Because in medicine, we keep on thinking about static images, right? But we also have dynamic imaging over time, whether it's looking at movement of, let's say, blood in human body, or also over time in terms of follow-up of imaging, right? So you have let's say, a cancer or whatever, and it changes over time, right? After therapy and things like that. So lots of great ways to kind of, bring that in as you see it, with all the vision work you do. So anyway, thank you. We're going to do a photo a session now. And so I'm going to ask everyone to turn on their cameras and join us. And then we'll have a short break thereafter. Ramsey, you're going to help us, right?
Yeah, if everyone turns on their camera, I can just snap a few screenshots. All right, waiting for a couple more to turn on the camera. All right. Smile. One more photo. There we go. All set.
All righty, that's great. So we have a break now, and then we'll regroup at 2:30. So you.
All right, it is 2:30, so let's get started. And this session is our AIMI industry affiliates session where they each have a chance to introduce themselves. And I think one of the reasons we all get involved in science and research is we want to create new knowledge, and we want to have that knowledge have an impact on the world in some way. And we have many options on how to have an impact on the world. We might publish the research in a journal where other scientists can use it and advance science that way. We can open source our code where other developers can use the code. We can start a startup company over some intellectual property that we may have created, and we can license our property to industry. We can cooperate with industry on translating it into the clinical setting or whatever setting it's useful in. And so that's why I think sessions like this are so important, and relationships with our industry partners are so important, is it's one of the main ways in which we do have an impact on the world with the research that we do. And in fact, some of the companies today have been spun out from Stanford. So we're delighted to have them all here with us today. And each presenter will have 5 minutes. It's informal. And we'll start with Nish Khandwala, who's the co-founder and CEO of Bunker Hill Health. Nish, take it away.
Thank you, Dr. Langlutz. Hi, everyone. It's great to be back. My name is Nish. I was actually a student at Stanford and worked with the AIMI Center as a student. And now I'm the co-founder of this company called Bunker Hill. And I wanted to share my screen with you today to tell you more about what we do here. So our goal as a company is to streamline multi-institutional collaboration, whether that's for multi-institutional training, validation, or distribution of algorithms. So let's say you're a researcher at Stanford who has now trained an algorithm using Stanford data, and you're now interested in seeing how this algorithm performs across different hospitals, across different data distributions. Today, there are a few steps that you'll need to do. First, you will need to work with the other hospitals that you intend to work with on data use agreements. These typically take anywhere from 3 to 6 months per institute. You'd also need to get an IRB approval at each site, and that also takes about 1 to 3 months per site. And if you're doing a prospective evaluation of your algorithm, you will also need to work with their IT teams to set up the infrastructure to deploy your model there. And that typically takes 1 to 2 months. After that entire process of many months, you will finally be able to start on your validation study or on your training study, effectively your multi-institutional collaboration. With Bunker Hill, our goal is to abstract all of that process away so that you can get started immediately on such multi-institutional collaborations. So Bunker Hill here builds a consortium that connects different health systems together for the purposes of multi-institutional validation, deployment, and training. So when a hospital gets into an agreement with us, they automatically get into an agreement with every other institution in the consortium. Stanford's already a part of this consortium, so today a Stanford researcher could train, test, and validate their algorithms on data from other institutes without signing any additional agreements, using our infrastructure, and using our existing umbrella IRB. Similarly, you could help your friends at other sites train, test, and deploy their algorithms at your site, again, using our existing infrastructure. The way in this works is that there are 4 ways to participate in this research network. You can upload your algorithm, you can help train an algorithm built by someone else by contributing training data, you can help validate an algorithm built by others, and finally, you can use it for clinical practice as well. When an AI researcher, whether that's a Stanford researcher, a startup, a large company, a pharma company, what have you, when they create an algorithm, they have the option to upload their algorithm to Bunker Hill, here shown in green. We identify institutions in our network who are interested in contributing training data to help improve the performance of that algorithm. And in exchange for their efforts, they get to use the algorithm for free. We then identify institutes in the consortium who are interested in validating the algorithm. Here, validation can be a retrospective standalone study, a prospective randomized control trial, what have you. And in exchange for their efforts, they also get to use the algorithm for free. At this point, the researcher can ask us to not distribute the algorithm at all, distribute it for free, or commercialize it. We will file for FDA clearance, And then if the option is to commercialize, we will sell it to other hospitals and share the revenue with the researcher, as well as with the hospitals that have contributed training data. A good example of this was the first project that we did with Stanford. Dr. Bhavik Patel, who is now actually at Mayo, but during his time at Stanford, led a project to develop an algorithm to predict calcium score on routine non-gated chest CTs. This was an algorithm that was trained and tested on Stanford data, and he was interested in seeing how it performed at other sites. So we worked with DASA, MedStar, and UCSF. These are large groups of hospitals across the country and also in South America to do a standalone multi-institutional validation study, after which these institutes now use the algorithm for free. This was later published in Nature Digital Medicine, and it was a successful project, and we're excited to support new projects as well. Today at Bunker Hill, we have 9 institutions who have joined the consortium: Stanford, UCSF, DASA, which is a group of 2,000 radiologists in South America, Rochester, MedStar Health, which is a group of 10 hospitals in the East Coast, University of Kentucky, Children's Hospital of Colorado, University of Colorado, and UVA. And we have many others that are in the rate of joining the consortium. And we have projects across the spectrum. We have cardiac imaging, nuclear radiology, mammography. We also have projects with oncology and pediatric algorithms as well as radiogenomics. So we're excited to support projects in the AI for healthcare space. And it's all free of cost for all researchers. So if you are a researcher who is building algorithms and is interested in working with other institutes, we'd be happy to support and facilitate that multi-institutional collaboration. Please feel free to reach out to me. My email's here, also is my Twitter handle. Thank you for your time and your attention.
Thank you, Nish. Thank you very much. And so at this point, I'd like to introduce Geraldine Miller, who's the Senior Director of the AI for Good Research Lab for Microsoft, which has been a great partner with the AIMI Center on our data distribution platform. So take it away, Geraldine Miller.
All righty. Okay, so I'm going to share a screen real quick and walk you through some things. Maybe I'll share a screen. It is not letting me do that. Give me a second. Okay. Okay. All right. Let me know if you see a screen. Can somebody
Yes, we can see it. Yes.
Perfect. Okay. So hi, folks. I am Geraldine. I am the program lead for the AI for Health team at Microsoft. I'm coming to you from rainy Redmond, where I'm sitting in an easy chair today. So with that, I was going to walk you through a little bit about what we are, just a program overview, and then talk a little bit about some highlights of the type of work we've done. So the program that we run is called AI for Health. It dates back to January 2020, which for many of us here feels like eons ago, right? That seems like light years in the past. But at the end of January in 2020, we announced the launch of this program through our philanthropies group. The goal really is to use artificial intelligence, data more generally, and analytics and visualizations to advance the health of people and communities on a global scale. It's a $40 million investment from a multi-year investment, so 5-year investment, and really focused on several types of recipients or what we call grantees. Nonprofits. We do a lot of work with different types of NGOs around the world, researchers from academia as well. Sometimes academic medical centers are keen on doing work specifically related to their health concerns. And then the currency that we bring as a program is twofold. We bring both grants of our cloud, Azure, so meaning giving people the ability to do the computational work they need to do to build these models without having to be worried from a budget perspective about cost overruns and getting the funding for the cloud infrastructure resources. And then we also bring data science resources as well from a collaborative standpoint. We take a portfolio-based approach. So we have kind of outlined 3 key areas in health. The first is quest for discovery, which is what really basic scientific research, right? So trying to light things up by getting a fundamental understanding of some of the areas in health. So it's a little bit of a broad term, but it gives us some flexibility to really invest in areas where we think the particular field is underfunded. Global health insights, you can think of this more of a shared common understanding of health and longevity, or what I would call population level data sets, analytics and analysis, and then more specifically in the area of health equity. So really trying to understand areas, both either from a geographic perspective or a population segmentation perspective, where there are these communities of vulnerable people who are, where there's a disparity in terms of the health services they receive and in terms of, their longevity, and to apply our artificial intelligence to understand the problem and help do some course correction. So, we quickly did a segue launching in January of 2020. That was literally about days before we as the Microsoft team went into, hey, nobody come back to campus. We're all at home for remote work. But we quickly took a pivot and added on a little bit from a funding perspective to focus specifically on COVID-19. So an additional $20 million, and included some focus areas. Again, Azure more generally to support the AI workloads, but also Azure HPC. Again, the portfolio-based approach kind of outlined to the areas at the right. So again, data and insights. This was really focused a lot on our modeling work that we do with Washington Department of Health, and more generally, a set of more general models that we produce and put out on the AI for Health website. Treatment and diagnostics, a lot of work in people using AI in the area of drug discovery, looking at vaccine development and therapeutics. Allocation of resources, trying to understand, again, these underserved communities and how resources were being distributed and whether or not that was equitable. Dissemination of accurate info. I think that one goes without saying. It's been a huge problem in COVID, and really trying to understand that problem at its roots from the data perspective. And then again, this category for foundational science research. And more recently, we've taken a pivot to focus on reopening as well, with the rollout and support in historically Black colleges and universities, and then in our own backyard in the state of Washington, with something called Return to School, which takes a pass at providing educational institutions and school districts data-driven decision-making. So dashboards, analytics, and visualizations to help them understand what's going on with their populations. So really quickly, just what is the AI for Health offering? Again, this is all philanthropy based. So these are grants of Azure Compute, and then data science, analytics, and visualization expertise through collaboration with the AI for Health team. The onboarding experience, I heard the gentleman from Bunker Hill talk a little bit about, some of the challenges in health. So the onboarding experience with these research collaborations includes a complete legal compliance and ethics framework that we take these projects through. And then the last point, and I'll end with that as the pivot, also elevation of our grantees' impact through communications. This is something we find very often in the nonprofits space in particular. There's people who are, there are nonprofits, there's limited budget for things like communications and storytelling, yet there is a huge upside from an impact perspective and in being able to get the message out. And so that is something as a tech company, a large tech company, that we can help with. And that's really about, just helping amplify the story that is going on behind the scenes around the AI. We tend to do grantee-led storytelling. It's in the voice of our grantees. They tell their story. It's the data. They're data scientists, and then their recipients of the work are the heroes in the stories. So we have about, I want to say we're somewhere around 150 grantees, around close to 300 media placements. Some of our CEO keynotes we had work featured in. We have work at our own executive briefing center. So we do a lot of rich visual hands-on storytelling about these grantees like Seattle Children, Novartis Foundation. And then we also did a whole kind of campaign around societal resilience and how artificial intelligence and visualizations and analytics really played a role in the pandemic and how society responded based on this data. So with that, that's me. I'm Geraldine, and it's a pleasure to meet everybody and to be able to share with you today.
Thank you, Geraldine, so much. Thank you for being here. Our next speaker is Christina Rombola, who's a Director of Medical and Scientific Affairs for GE Healthcare. And as many of you know, GE, we have a very large partnership over 5 years that's supporting 5 collaborative projects, and many of us working in those projects. So we're delighted to hear from GE. And Christina, take it away.
Thanks so much, Kurt. We're super happy to be here today and very thankful for the collaboration that we have with the AIMI Center. So I am just going to share my screen quickly here.
We can see it.
Okay, perfect. So as Kurt mentioned, we have a great 5-year partnership with the AIMI Center and GE. And Kurt, you mentioned at the beginning about partnerships and why they're so important. And we very much believe that too. We see ourselves as inventors and great builders of tools, but we really can't build products that matter to patients if we don't partner with folks like Stanford and the AIMI Center to bring in that expertise, both technically and scientifically, but also clinically. So what I'll do today is to share a little bit more about our collaboration as a whole. So what we've done now starting, we're about a year into projects now. What we did was decided, hey, like what is GE really great at? Well, we're really great at building medical imaging tools, things like MR, CT scanners, PET scanners. We also build baby warmers and patient monitors, but a big part of our relationship with Stanford as a whole is around radiology. Stanford has some great expertise clinically, scientifically, and technically. So can we really build teams together that can focus on solving relevant problems in this kind of upstream AI space? From a GE standpoint, we see that there's a lot of companies and a lot of great teams out there that are doing a lot of great work downstream. But we found, and we see ourselves as being uniquely positioned in the market to be able to make a big impact incorporating AI into the things that we're really good at, which is radiology devices. So the way that this collaboration works is actually a bit unique compared to other things that we do. So we've built teams that are interdisciplinary, and both GE and Stanford faculty and folks on a team. So there's clinical expertise, there's scientific expertise, there's engineering expertise, both in MR, CT, a new team in the PET CT space, a little bit further upstream on the protocoling side of things. And then underneath that, working with Kurt and his team as well on advancing and figuring out how do we actually build all this infrastructure to enable the AI development that we're seeing from these great teams. So a little bit about what that looks like is this very remedial slide here, but it just shows the breadth and depth of the number of folks that are involved in this collaboration, which is what we really cherish most. You can see here that there's individual modality teams, so the GEMR team, CT team, but you'll also see folks from a big part of our digital business and our AI platform business, as well as a big scientific team that we have down in Menlo Park at ASL West, which is just a hop, skip, and a jump down the road. So while we have these individual modalities that do great work, this particular collaboration is very unique to us because instead of working in silos, it brings a number of people at GE and a number of different businesses together in one place and allows us to collaborate not only with the AIMI group, but with also big teams at Lucille Packard, the School of Medicine, and Stanford Healthcare. So we're just super grateful for the partnership that we do have with AIMI. They've very much been an integral part of our own AI journey. And just thank you so much for the work that we're doing today and will continue to do into the future. So thank you all.
Thank you, Christina. Thanks for that overview. Our next speaker is Tanvir Saeed Mahmood, who's an IBM fellow and comes to us from IBM. Our relationship with IBM was developed through IBM's relationship with HI, the Human-Centered AI Institute here at Stanford. And Tanvir's been an active collaborator with many of us. Tanvir, please take it away.
Yes. Hi, this is Tanvir Saeed Mahmood. I'm from IBM Research and I'm an IBM fellow. As Curtis said, I've been associated with AIMI Center for a few years now, and we have an active collaboration going So I'll mention 2 or 3 projects that we are doing. So unlike perhaps the other sponsors or funders, we are primarily a research organization, and the kind of collaborations we have are conducting research for advancement of science purpose. We don't necessarily have any commercial purpose in mind in doing these collaborations. So one of the projects that we've been actually pursuing is with Dr. Heike Dalrymple and Daniel Rubin, and on pediatric lymphoma, and essentially about a clinical decision support tool for automatic scoring called the Deauville score, so computation of that. And this requires addressing some challenging problems in fusing multiple modalities of PET and MR to localize lesions and then measure their volumes in comparison with other anatomical structures. Now, since these lesions could be anywhere in the body, it makes it challenging to develop segmentation algorithms that are generalized and independent of anatomical location. So we've been developing several multimodal fusion techniques to do that. The core underlying algorithms come from this project that we have at IBM side on multimodal fusion AI. And so several of our algorithms time we have on any of these. At a very high level, I'll also mention another project that we do at Stanford High and also involves some members from AIMI. And this is a neuroscience and AI project in which we are trying to model the human declarative memory system in brain and trying to...
Tanvir, you may want to turn off your video. I think your bandwidth is limited. Tanvir?
Can you hear now?
Yes, go ahead.
Okay, you can hear me now. And then
Yes.
I guess the slideware would probably also lower the bandwidth. Yeah, so I was saying the second project is more on a neuroscience and AI and bringing it in the context of assisting patients who cannot recall events. So this is for memory prosthetic aids for recalling events is one of the areas. So for both of these, we have had interns this year. And so we hope to continue the collaboration for both these projects through the interns. Of course, we also have members of AIMI actively involved, hopefully a bit more actively involved in the MICI 2023 forum that we will be running as a conference with clinical involvement, heavy clinical involvement. MICI is actually running this week, so some of you may be participating over there as well. And I think some of us are also involved in the American Board of AI in Medicine and trying to increase and then hopefully influence the adoption of AI algorithms. So those are primarily the long activities that we've conducted, and many of our research is published. So most you can take a look at some of those publications. I'll just push up one slide that talks about these so people can get an idea of and track them down. Let's see if I share screen. Algorithms, we look at some of the old statistical techniques such as canonical correlation analysis and developing sparse embeddings. So for those who are working in encodings, you can see some of the latest developments that are bringing together traditional statistical literature with AI literature in the sparse graph CCA work that we published at ISB this year. There is a new method of fusion for when you have uncertainty in the learners itself that inherently exploits the uncertainty of the learner. So in some sense, it's the variations in your learning capability that's actually exploited to develop a more robust learner. So this method of uncertainty-based fusion is something that we also published at ISB this year that you may want to track. Another work that tries to combine work from multiple modalities such as imaging and genomics is a feature that is appearing at MICI this year, where we showed that you can actually predict the functional relationships between genes to imaging features. In this particular case, the PLN gene 12E sphericity for cardiac genes as well as Manhattan plots. So some of these require some interesting techniques of cross-modal association. So feel free to check out is to fuse information from multiple modalities and looking at those algorithms. So I'll stop here and see if there are any questions.
Great, thank you, Tanvir. Thank you very much. Our next affiliate is Nines Radiology, which I believe was one of our very first industry affiliates. And we have Nand Dalal, who's a senior machine learning engineer at Nines, to present today. Nand, take it away.
Thanks for the introduction. I'll just share my screen really quick. All right, are you able to see the slides?
We can see it, yep.
Great. Yeah, so thanks for the introduction. Nines is a teleradiology clinic where radiologists and engineers work side by side to build the most robust medical diagnostic cloud. My name is Nand, and I'm an engineer at Nines where I'm working on applying machine learning towards this goal. At Nines, among other things, we built FDA-cleared algorithms for worklist prioritization and workflow improvement. And through this, we've built robust processes for developing computer vision and NLP systems for radiology. One of the things we learned to be a key component beyond the ML algorithm, though, is integrating it into a radiology workflow. And this is how we can realize the effects of our models and help improve patient care. So we've built out the Nines teleradiology clinic with the thesis of improving radiology by having radiologist engineers work side by side. We're working to unify technology in medicine by building the most efficient and reliable vertically integrated medical diagnostic cloud. So Nines owns the full radiology workflow from receiving studies via DICOM and HL7 to sending back final reports signed by Nines radiologists. And this allows us to rapidly iterate on the radiology workflow. For example, our engineering team can ship updates multiple times a day, unlike traditional companies in medicine who have to ship code every few months. And so we've built many improvements, but for the sake of time, I want to just take two examples of machine learning-based radiology workflow improvements that have been enabled by our vertical integration. So the first one is related to efficiency. It's study validation and contrast dose checking. Currently, radiologists have to determine whether a study is ready to read or ready for review before actually reviewing the study and dictating the report. But at Nines, we believe that when a study reaches a radiologist, it should be completely ready for review. One example of this is contrast dose. Like certain CT and MRI scans are performed by administering contrast, and radiologists need to have this information included in the final report. However, there's no standard for how to send this information in DICOM or HL7, and there's no standard for like the format of the contrast information. But using NLP, we're able to determine whether the necessary contrast information is present, or whether it's been provided, and if not, we can send an alert to a radiologist assistant to contact someone at the hospital for the information. And this helps improve the efficiency of the radiologist and reduce their burnout. So this is just an example from the Nines system where the system opened, we automatically opened a missing contrast issue. So a radiologist assistant acknowledged it and resolved it by contacting the hospital for the contrast dose. So that's on the efficiency side. And what about the reliability side? There can be surges in the hospital which result in lots of studies for the radiology department. And this can lead to undesirably long turnaround times. So we built a system to detect these surges and send an alert to our clinical operations team to potentially bring on extra radiology help to make sure we can keep up with the volume and maintain reliable turnaround times. This combines a reading time model and a volume forecasting model, which can also help efficiency since it allows us to keep a lean schedule. We worked with our radiologists to iteratively improve the performance of the system and now have an automated process to monitor the performance of the models and identify when they need to be retrained. So at Nines, we're excited about the improvements we can make by having radiologists and engineers working side by side. And these were just a few examples of improvements that have been enabled by vertical integration. And we have many more that are currently in development. We're always open to collaborations with academia, so please reach out to me if you'd like to discuss real-world applications for radiology AI. Thanks.
Thank you, Nand. Our next presentation is from Google Cloud. And I know many of you have been recipients of our Google Cloud credits program. And so we have today Tom King, who's an account executive, and Eliezer Ortiz, who's a senior program manager, to present from Google Cloud. Please take it away.
Thank you, Kurt.
Tom, we're not hearing you. You may be muted. We can see your slides. Tom, we're still not hearing you. I heard you for a moment and then you went silent.
I can kick it off while Tom solves his microphone issues. So hi everyone, thank you Kurt for having us here.
Sure.
I'm Eliezer. I'm a program manager at the Google Cloud Public Sector team, and Tom was set to kick off the introduction, so I'll hold that for his conclusion. I would just like to provide a summary for you in terms of our existing collaboration that you mentioned, Kurt. So far, we have funded 13 research projects for $234,000 in Google Cloud credits, meant to help researchers at the AIMI Center drive their breakthrough scientific research. This program is still available, and if anyone is interested, I urge you to reach out to Joanna and Stephanie Bogdan with interest about accessing these credits. In addition, Tom, if you are hearing me and you can change to the next slide, he is available. I do also want to share visibility with you all about the Google Cloud Research Innovators Program, which kicked off its inaugural cohort this year. This program is meant to establish a very small community of researchers that are driving breakthrough research work globally. This is a group of about 30 researchers spread throughout the globe that are working with Google Cloud to help them drive amazing, incredible work with our solutions, and also in collaboration with Google. So essentially what this program entails is enabling and providing support to researchers with direct Google Cloud technical engineers, over-investing in Google Cloud credits for their work, and also partnering with them to get access to additional funding sources, additional visibility of their work and publications. We are scheduled to launch a new call for nominations in November for the next cohort, and we urge everyone to participate. So, Tom,
sorry about that all. You know, the Zoom really doesn't normally give me trouble. Can you hear me now?
Yes, we can.
Okay, sorry for the glitch there.
No problem.
Thank you, Eliezer. So a couple things I wanted to highlight. Number one, thank you to the AIMI community in Stanford for your support. We've really been pleased to be a part of the industry group over the past year plus now. A couple things I just wanted to bring out was Google Cloud's support of COVID-19 research across Stanford and other institutions during these challenging times. In our partnership with the Harvard Global Health Initiative, we funded over $20 million in research projects. We also supported states with vaccine distribution. We supported the ability to help people get back to work, adding infrastructure and capabilities for them to be able to use those resources at the state and local government level. We're always happy to talk to folks and share some knowledge and things that could be of benefit and help. We have a few events coming up that you might find interesting. Next is going to be virtual again this year, but you can register and have access to all of the content. It's going on October 12th through 14th, and you'll find the link here. It's g.co/cloud next. And one more advance, Eleazar, please. On the next slide, we'll talk about our Government and Education Summit, which is going to be a forum for your peers to highlight some of their stories and what they're doing with Google Cloud. We have Lorraine Nelson from Stanford's Population Health Sciences who will talk about what she's done during the COVID-19 pandemic and how Google Cloud has helped her along that journey. So we hope you'll join us for this 2-day event, again, virtual. You can sign up. All of these are free and have access to the material either as it's presented or after the fact. This one's at cloudonair.withgoogle.com. Again, thank you all for your support, and we look forward to working with you in the coming year.
Well, great. Thank you, Tom and Eleazar, for your agility in response to some technical problems and for all of your support. Appreciate it. Our last presenter today is Enhao Gong, who's the co-founder and CEO of Subtle Medical, one of the Stanford spinoffs that we mentioned earlier. Enhao, please take it away.
Thank you. Can you hear me?
Yes.
Yeah,
we can see your slides too.
Oh, that's great. Yeah, just quickly go over. I don't want to stuck into the slide details, but it's really great to have this opportunity to talk to you all and to introduce Subtle. So as many of you know, Subtle started from the research we did at Stanford. We really want to use AI to make imaging faster, safer, and smarter in a way to accelerate the world access to better healthcare for especially high quality radiology exams. And when we found one of the pain points we really try to solve is there's a lot of value in imaging and increasing demand for sure, especially during the COVID. There are many more backlog in different hospital imaging centers of the imaging exams. But on the other hand, both provider and patient, with something unsatisfied for long waiting time, for the limited capacity all their existing scanner can give them, they have to try to find a way to solve the issue created by aging fleets of scanners, long waiting time, and discomfort. We all believe in AI can really transform and making the imaging faster and smarter. So in this way, we kind of convert a lot of our research. We licensed IP from Stanford to found this company at Subtle Medical. We really want to provide unique AI solutions to transform, especially the upstream opportunities. I think a lot of great startups are working on like image classification, detection, try to solve the diagnosis part. We think it's fundamentally great, but there's for sure unmet need to improve the image acquisition and enhancement. So that's where we have unique solutions, because we find that's the benefit we can provide to the patients with faster exams, make sure they don't have to wait that long. And we have validated with our clinical study shows clear clinical and financial values for hospital imaging centers we partner with. And this fundamentally also built by the team. A lot of people are familiar is coming from Stanford side. I co-founded with Dr. Zahachak, who is also part of AIMI as well, licensed and IP and has ongoing collaboration with a lot of Stanford researchers. And the team is also not only just driving technology, but to see how we can transform technology into clinical impact with the industry veteran to understand how to convert the technology into products and convert the product into commercialization. I have to say, in the last maybe 3-year journey, after my PhD from Stanford Radiology and Electrical Engineering, I learned a lot from the journey and get a lot of help from Stanford, especially AIMI as well. So we really look forward for more collaboration, and both in research and in partnership side. And our primary technology and products is Subtle PET and Subtle MR. In short, just make it easy to understand is we have AI to boost the efficiency and quality, make it faster and safer. And we have multiple clearance in different regions, including US and Europe. And we really look forward to bring our technology to more hospital imaging centers around over the world. So that's where we try to scale. And last but not least, I think this fundamentally, we really thankful for a lot of both collaboration and advice from our advisory board. Many of them also with have Stanford affiliation as well, to really help us to understand not only how to build technology, but what are really pain point, what is the like what kind of solution we should further improve to make sure we really benefit both radiologists and patients and our customers as well. Yeah, so with that, we're further looking forward to expand to more modalities and globally as well. So I think don't want to take too much time for everyone, but I really look forward to learn more from both the advanced study from AIMI side as well as how we can further collaborate. Thank you.
Thank you, Enhao. Well, that concludes our industry affiliates presentations for today. I just want to thank all of our affiliates, those who presented and those who didn't. We have over 15 now of industry affiliates. Thanks for your partnership. Thank you for your contributions. And thank you again for your presentations today. At this point, I'd like to turn it over to our career transitions panel that will be led by two of our postdoctoral scholars, Natasha Shaybani and Rohir Vandersluis.
Hello, everyone. So I just want to thank everybody on this call for the really fascinating presentations and participation so far in the retreat. It's my and Rohir's treat now to introduce our panel discussion, which is going to be about career transitions. I'm a postdoc in Daniel Rubin's lab, co-advised by Ash Alizadeh in oncology. And so with that, I'll turn it over to Rohir to introduce himself and ask our first panelist to do so as well.
Thank you, Natasha. For those who don't know me, I'm Rogier van der Sluis. I'm a postdoc at the AIMI Center. I'm supervised by Kurt Langlaats and co-supervised by Akshay Chaudhary. I started my postdoc during the pandemic, so I'm really thrilled to meet many of you for the first time tomorrow. And as Natasha already said, we're very excited to moderate this session on career transitions. We have 5 great panelists today with various different backgrounds, including academia, industry, and entrepreneurship. At the start of the session, we will give each panelist the opportunity to introduce themselves, and then we will proceed with various questions to learn from their career decisions. The last 20 minutes of the sessions are reserved for questions from the audience, so make sure to post your questions in the chat during the conversation. So let's kick the session off with the introduction. Akshay, could you start to introduce yourself? And while doing so, can you give us a short overview of your current and previous positions in your career?
Yeah, absolutely. And thank you for Natasha and Rohir for having me on this panel. So I'll try to give a quick summary of how I got to where I am without trying to bore everyone in the process. So I started off with an undergraduate degree in bioengineering, which was at UC San Diego. And over there, I tried to get involved in as many different types of research. I did some research in systems biology, some biosensors, and got into medical imaging only over the last 2 or 3 months. But I realized, wow, this is really cool. There's a lot of technology that's involved with it, and there's a lot of room for clinical application, which is what inspired me to go to graduate school right after my undergrad to work on my PhD. My high school and my undergrad was in California, and I realized I did not want to leave the nice sun and the nice weather, so I decided to stick around, and I just moved up north to Stanford, and I have been here ever since. I started on my PhD in 2012. I wrapped up in 2017. That was in the bioengineering department. And I probably did what everyone would recommend you not to do, which is to stay more or less within the same group for my postdoc right after my PhD too. And my reasoning was I really enjoyed the people. I really enjoyed the research. So I didn't want to change for the sake of changing. I did decide to teach myself a completely new set of skills. My PhD was primarily focused on MRI acquisition, but I figured that my goal for my postdoc would be to try to become an expert in machine learning. So that's what I've been trying to do over the last few years. So that's how I justified not moving, but at least moving to a different research area. And during that time, I was still pretty confused about what I wanted to do with my life. I wasn't sure if I wanted to stick around in academics or go to industry. So I tried to have a little bit of both at the same time. That's when I started consulting with different companies just to see what life might be like on the other side without necessarily committing one way or the other. And I think that was a really valuable experience for me because being in industry was nothing that I had done previously. So it gave me a sense of what the day-to-day life might look like. And I ended up realizing that I really enjoy pure research a little bit more. I think there's definitely value in creating products and bringing them to the market. But my interests are more on the asking why questions and spending more months than one needs to trying to answer those why-based questions. So that's why I decided to stick around. And I became an instructor at Stanford. And last October, I transitioned to an assistant professor. So that's my journey where I didn't really rock the boat too much and just stayed in the same place.
That is fantastic. Thank you for that introduction. And we look forward to hearing more from you very soon. Dr. Rusu, why don't you go next?
I think my training, and thank you all for the invitation to talk. My training has been a little bit more into rocking the boat as much as I could. I really moved a lot. I moved across fields. I moved across industries, and I am at Stanford now. So I'm kind of happy about it. So let me tell you a little bit how I started. So I was always kind of interested in math. And as I started, I got interested in computer science. That's when I was in high school. So I decided to do a degree starting in engineering. I figured that's probably the best way to go about it. And then slowly I progressed towards biology. It's like, oh, that's interesting. How about I do that? I don't know. Sounds interesting. And then it kind of went, that's kind of the theme of my entire career and transition has been, oh, that sounds interesting. Let's move across the other ocean and the other continent. And I think throughout my career, I moved across two places in undergrad. So I did my undergrad in France and I did an engineering degree. I specialized in bioinformatics and modeling as an undergrad. Then I decided to come to United States. I did my PhD in the University of Houston in structural biology. So I don't have a medical imaging kind of training, but I do have a data analysis background. And then as I was doing the structural biology work in my PhD, I was like, ooh, medical imaging, that sounds interesting. I could probably go ahead and do something with all the skills that I got, a little bit more useful than trying to solve the structure of a protein, at least more tangible and quicker. So I did move in my postdoc in medical imaging, and I was always kind of a little bit curious what's on the other side. So I decided at the end of my postdoc to go in industry. I spent about 3 years working for GE Global Research, as that's the R&D center of GE. And at the end of those 3 years, I decided, or essentially the opportunity came and I decided to go for it. And that was this position at Stanford. So I've been now at Stanford for 4 years. I have a lab that is ever growing. I'm very, very excited with their accomplishments and their research progress. And I'm more than happy to talk a little bit more about each of the steps that I've mentioned. I did move in US in 5 different states. I lived in 5 different states: Texas, New Jersey, New York, Ohio, and now California.
Wow, thank you for sharing that. Great journey. Yuhao, you recently made a career switch. Can you tell us something more about that?
Yeah, sure, of course. So first of all, I'm very happy to be here. I see a lot of familiar faces. Hello, everyone. So my name is Yuhao. So I was a PhD student at Stanford in the biomedical informatics program. So I just graduated earlier this year in 2021 amid the pandemic. So, and then right now I'm a scientist at Amazon AWS AI. Working on general like AI solutions that we created for AI services were created for enterprises. So, but let me go from the very beginning. So I did my undergrad back in China, so it's a different country, and I also make a lot of transitions in terms of the industry or research direction. So I did my undergrad in EE. We call it electronic engineering, not electrical engineering. That's in the US. But I study a lot of the hardware and also signal processing type of thing. But during the undergrad, I was exposed to a lot of like programming and software engineering type of thing. At that time, I got to realize that I was more interested in software rather than all of the hardware type of stuff. So I made the transition when I applied for the graduate study. So I did a master study in computer science at Stanford at the beginning of my time at Stanford. So, but then during that time, I got exposed to a lot of the biomedical applications by working with a professor called Mark Newson, and as well as the professor Ross Altman in the BIMI program. So it was that time I kind of realized, oh, there are a lot of interesting applications of the AI stuff that we studied in the CS program in the biomedical field. So that got me motivated to actually apply for the PhD program in biomedical informatics. And then after I entered the PhD program, I got to know Kurt, who is also here today. I'm very happy to see him again. And my PhD was actually advised by Kurt and also co-advised by Chris Manning in the CS department. So I did my PhD in applying machine learning and natural language processing to medical text. So my thesis was on understanding and generating medical text. So that was a very interesting journey for me. And also, I also spent some time working on imaging and also multimodal learning between the text modality and imaging modality. And then after I finished my PhD study, I became very curious about how AI and machine learning are actually applied across different industries. How was they applied in, for example, finance or some other industries, and how can we make the value out of it? So that's when I was opposed to some opportunities to become a research scientist at different companies, and I finally chose Amazon AWS AI. And right now we're working on enterprise level AI applications. We cover different industries. Medicine is one of them. So we actually build NLP solutions for some medical applications, but not only medicine right now. So we're also build AI solutions more general for example, like finance industry and other industries nowadays. Yeah, so that's my journey.
Wonderful. And next, I'd like the person to go whose work at Stanford set a really important groundwork for my own postdoc, Dr. Sarah Matonen. Please, you have the floor.
Great, thank you so much. And thanks for the organizers and the invitation to speak. It's great to see so many familiar faces, as you have mentioned, and it's great to be back. So yeah, I had a little bit of a windy road to get to where I am now, but I can give you a little bit of a background. So I'm from Canada, Ontario, Canada, so just outside Toronto. I did my undergraduate degree at the University of Western Ontario, which is in London, so just west of Toronto. And during my undergraduate degree, I kind of took a little bit of everything. I ended up with a degree in medical sciences, so it was a little bit broad. I didn't really know what I wanted to do, but I kind of knew I always wanted to do something with cancer. So I decided at the end of my undergraduate degree, I was going to switch gears a little bit, and I went and did a degree in clinical radiation therapy. So I trained to be a radiation therapist to treat cancer patients, and did a 3-year degree there. And as part of that program, I did a research project, and that's really where I fell in love with the research aspect of it. So after that 3-year degree, I decided to switch gears a little bit, return back to the University of Western Ontario to do my graduate degree. So I really fell in love with the medical imaging aspect as part of that program. So then I decided, as part of my graduate studies, I was offered a project looking at image analysis and machine learning applications in medical imaging. So I jumped on that and kind of switched gears a little bit to do more of the programming, and started out there with that. And then did my PhD at the University of Western Ontario again. So as you notice, London kind of keeps coming back. I go back and forth between London and other places. And as Akshay mentioned, I got the advice that if I ever wanted to return to London, I needed to go somewhere else to do a postdoc. So I ended up looking at different postdoc opportunities and decided to do a postdoc with Sandy at Stanford. So I did that from 2017 to 2019. And I always knew I kind of wanted to end up back as an academic. So I started applying for positions, and lucky enough, got a position back at Western University in London. And I've been an assistant professor there for the past 2 years, since July 2019. So I look forward to discussing it more shortly.
Thank you. It's great to hear so many different stories already. And there's one more left. Nish, you already talked a bit about your company, but can you give us a bigger overview of how your career path went?
Of course. Thanks a lot for having me here. Yeah, I did my, as I mentioned earlier, I did my undergraduate and graduate studies at Stanford. I came in in 2013. And in my sophomore year of undergrad, there was a new class offered by Fei Lee's group called CS231N. And I decided to take that, which is deep learning for computer vision. And back then it was only 100 people. Now usually it goes for 700 people a quarter. So it's grown dramatically since then. But after taking the class, my goal was to get an office on the second floor of Gates, which is the computer vision lab at Stanford. And during the course of doing research in those labs, there was an AI salon hosted by Professor Vijay Pandey, who's a biophysics professor at Stanford, now a venture capitalist. And he mentioned how AI for medical imaging was a solved technical problem, but was not actually something that had seen the light at the end of the tunnel. And that was very unsettling for me as a realization, where the technology seemed close enough, but there seemed to be no efforts to be taking those algorithms into clinical practice. And really just, I was trying to understand what were the bottlenecks. Coincidentally, that in those months, there was an email sent out by Chris Ray's group asking for research collaborators who were interested in coming up with weak supervision techniques to efficiently extract labels from radiology reports to label radiology images. And I took on that position, and I really enjoyed my time there. And at the end, we published our papers, realized that, okay, it seems like getting labels efficiently is no longer going to be a bottleneck for developing new algorithms. And around that time, ChecksNet also came out. And so did the Bone Age paper from Dr. Halabi and Dr. Larson's group. And that really spun up another thread in me, which was, okay, now that these algorithms, at least they're proof of concept algorithms, what's really stopping them from being used in practice? And that led to my friend and I reaching out to Dr. Langlotz to see what it would take for Stanford Hospital to start using the algorithms that were developed by us during the course of our research, and also ones that were built by other folks in the AIMI Center actually into clinical practice. And that led to my friend and I organizing a randomized control trial for one of the algorithms that Stanford had built. Realized that it was incredibly painful to work with multiple institutions and collaborate. And that led to the formation of the company. So I guess I did change a lot of hats, but in the end, I have been interested in AI for medical imaging since roughly 2016 now. But I've been wearing multiple hats and changing those hats every now and then.
Excellent. So now that we've gotten to meet each of you in a little bit of detail, we'd like to delve a little bit deeper into your personal journeys in getting to where you are today. And so I'll open up this question to anyone on the panel who would like to start. How did you prepare yourself for the career path you chose? And what other options did you consider at the time? And I guess just to dovetail off of that, I do see a question from Sandy Nepal in the chat as well, which mentions, how did you know you made the right choices for you? So a few different questions floating around here, but I invite anyone to begin.
I'm happy to take a stab. Maybe I can start
Sure.
with Sandy's question first about how did I know that I made the right choice for me? I never did. I always felt that it's an exploration process, and the only thing I can control is who are the people that are around me. Do I enjoy working with these people, and am I happy in the short term? I don't think I can predict what will happen in 5, 6, 10 years time. So the only thing that I can control is my immediate future. What are some of the projects and the people that I work with, and trying to make a bet on that. So I always knew that I'd made the right choice retrospectively because things just worked out in the long run. But besides that, there's no wrong decision, and there's always different decisions that you can make. And sometimes you just have to go with your gut feeling and do what seems most exciting for you.
maybe I can follow up to Akshay's point there. I, like him, I don't think I ever know whether this is the right decision or it has been the right decision. But I can tell you a little bit of how I made my mind about some of these decisions. One of them was kind of as I was attempting to finish my PhD, I was thinking about what's going to follow for me, right? I could have the choice between going to a postdoc or not, or go to a different postdoc, different field. And I stayed on that thought for quite a little bit, mostly because I was scared, to be honest. I mean, going in a completely new field, it's scary because first of all, I didn't know anybody. And second of all, so I couldn't use my network very well for that. And then second of all, it's like, what if I don't make it? But one of the things that I thought about was, what do I want to be when I, quotes in quotes, grow up? So I really thought about that 5-year plan, which I hated. I hate that question in an interview. But at that moment, it was, what would I really want to do as a job? Now I'm done with the PhD. What is the job that I want to do? And that will help me do what I want to get, where I want to get with my life. And one of the things that I thought is that I want to be in an industry, or I want to be in a field where there is an industry. And my PhD didn't feel like had an industry, at least not much of it. Hence the movement towards the medical imaging. I like the medical imaging field, but the push towards it was because there was both an academia option as well as an industry option. And I obviously got to use and check both of them. So that was one moment. So I thought about what skills do I need to get to that particular job that I envisioned at that moment in my head. That was the perfect job for me. And that was, I needed skills in medical imaging. So that was the first thing. And then the second thing is, once you actually get that job, how you decide is that if you accept or not accept that offer. Because again, it's a little bit unclear. And I never rushed to make that decision. I really took my time. If they gave me 2 weeks, I sat on it and I took the 2 weeks and never really thought hard about it. I just let it be in my mind and see if this is kind of, always was in the back of my mind, but is this really the decision? Is this the way I want to take it? And I kind of always went for it, but because obviously I applied for that job for a reason. But point being that it's really hard to know what the future will be. But unless you try it, you're probably going to be always worried that what if? So I don't like the what if scenarios, so I go for them.
I think that's great advice. Does anyone else wants to chime in?
I can add my perspective. So I would say that particularly to the question about making the right choice, right? So I think as a machine learning researcher, I think the right word as a metric is a little bit fuzzy. So it's not a good metric, or it's not the best metric that we can come up with. So I think everyone has a different definition for what's right, right? Somebody might want to optimize for the financial return, right? Which is completely legit, and it could be a good metric. And some other people, for myself, for example, I would like to optimize the metric of the happiness and the excitement for what I did or what I'm going to do, right? So I think the first thing there is to think about what is the metric that you want and the metric that you think you want to optimize for, right? So there's no like right or wrong in doing this, but rather to think about what is the more clear objective, or to measure whether you want to stay or do whatever you want to do, right? So and then for me, that's the excitement for the stuff that I was doing. So an example for me personally was I was studying EE again during my undergrad, and that was the time I realized that it's really not the industry that I want to spend most of my time on. So that's why I made the transition towards learning more about AI and software, and I feel that when I was working on AI and working on improving the algorithms for whether doing imaging or natural language processing, I can feel the excitement, and I feel like I can invest most of my time into the work that I do, and I feel happy about the work that I do. I think that's what's really driven the transitions that I have been making. So that's my personal perspective.
Wow. Yeah, that's like that's the typical computer science way to think about it, and I think it's perfect for many of us here. So thank you for that answer. How did you, like, another question to all the panelists here is, how did you prepare for, like, when you finally found out what you wanted to do, how did you prepare yourself to get there? I heard a little bit about that from Mirabella already, but probably someone else also has some ideas about that.
Yeah, I can start us off and kind of picking up on the previous question. Yeah, so for me, I echo a lot of kind of what everybody else had said in terms of finding what I'm excited about, what I enjoy working on every day, and the people that I'm working with and the problems that I get to solve. And I think, like, I look back at my career trajectory, and some people could say, oh, well, like, why did you do radiation therapy? Like, that was a waste of 3 years. You didn't really use it for anything. But really, like, I don't regret any decision that I've made. I think every path that I've taken has kind of built me as a person and kind of built my future as I've gone through, and kind of you learn from it in terms of what you like and what you don't like. So I think it's all valuable experience. And today I work on all these radiotherapy projects, and that background has been super, super helpful. So I think you kind of build off of that. And in terms of preparing, I think for me, I knew I wanted to go into the academic path as soon as, like, during my graduate school. And for me, what I needed to do to be successful was put myself in the best position to be successful. So finding, for me, mentors that were really invested in my success and helped me get there was a big part of it. So my PhD mentor and my postdoc mentor, obviously, in terms of getting to where I needed to be. So I think that was one important thing. And then just taking advantage of different opportunities in terms of, for me, I'll just point one thing out in terms of preparing for a faculty career. As Stanford, I think being a postdoc there provided me with so many opportunities to get to that next step. So like preparing for faculty's career course, going to different academic chats and things that were put on by the Postdoc Association also helped in terms of different steps along that academic pipeline to get to where I needed to be to get that job offer at the end.
I think echoing that sentiment as well, I think it's incredibly crucial to find people to work with who are very driven and motivated and inspire you. And at the same time, also find people who not only just want to mentor you, but sponsor you. I've been really grateful to have people who have sponsored their reputation, their time and resources to allow me and my collaborators to take on projects that otherwise would not have been opportunities available to us. So I think it's a cheat code in life and it's something that if you're lucky enough to find people to be sponsors, and there are many people on this call today who have been sponsors for my work. So yeah, if you're able to find those people, you're already on a head start there.
I'd really like to echo this sentiment of trying to find good mentors, because as I think about what skills I needed to develop, I think it always boiled down to two things: things that I knew I didn't know, and things that I didn't know that I didn't know. So I really looked to my mentors, especially starting off in the new field, to tell me, what are things that, a successful PhD student in MR imaging should know, because they're the experts, they've seen it all. And one thing that I really appreciated going over with my PIs, which were Brian Hargreaves and Gary Gold at Stanford, was every 6 months or so, we would just go over my CV and try to think about big picture perspectives as to what are my ambitions, what is working, what is not working, what are some skills I'd like to develop. So I really enjoyed having those conversations because it helped me think about the bigger picture. And when I was just starting on in my first, second, and third years, I really deferred to my PIs in trying to help me in learning new skills. Maybe it's understanding about how different pulse sequences work, or trying to understand how the reading room is. But over time, once you immerse yourself in that scenario, once you start going to a few conferences, you start seeing holes in the field that could be amenable for new research ideas. And at that point, then I could help answer, what are some good things that would be helpful for me to learn that would be impactful for the field? So I think it's a joint process where sometimes you have to defer to others, especially if they've been in the field for a long time. But at the same time, you also want to be able to put yourself out there and just try to learn about what are the problems in your field and just try to take a stab at them.
I think this is all amazing advice, and I hope I speak for everyone here by saying that I'm blown away by the feedback that's been given here, and to echo what Nish said about cheat codes, I feel like you all just handed us a lot of the cheat codes that can lead to success in these respects. So, you've all been incredibly successful in the settings that you're in currently, and I'd like to pose a different question that perhaps might be a little provocative. You've talked about your career transitions to date, but we wondered, do you see yourself making any other career transitions in the future? We've talked about leaping between academia and industry, and so I'd love to hear from any of our panelists about whether they foresee any straddling of those lines in your respective careers in the future.
I don't think I have a $1 billion idea lined up, so I foresee staying in my position for the near future. And my bosses are listening, so maybe I shouldn't say that.
So I mentioned it might be a little, little tricky to answer, but that is totally fair.
Yeah, I think for me, I think for me personally, because I'm working on machine learning or natural language processing research, I think one advantage of being in that position or in that field is that it's not only one industry, right? So we're actually applying the same set of techniques to actually solve problems in different industries. So that naturally gives me exposure to problems in different industries. For example, the model that I build for natural language processing nowadays could make an impact in life science. Or another day, the model that I build for processing natural images that people upload in their photo booms or whatever type of software, the same technique to process that is applicable to medical imaging. So it naturally provides me with the opportunity to expose to different industries. So I think because of that, I don't intend to make transition in terms of the industry. Unless one day we see that machine learning is dying and is not a thing anymore, I think that's going to be another story. But as of today, I think, I don't see myself going to make the transition into different industries. Yeah.
Maybe I can follow up. So on my side, I think my big point is that I would like to save one life. That's one of my goals and has been for a few years now. And I'm not yet there. I don't think my research has saved or helped save a life, which is a big word, save, but at least improve. So from my perspective, whatever gets me there, I will probably go for it. And it will probably be somewhere at the border of the two, because I do think both have advantages and disadvantages. And then I will make sure that I'll find a path that allows me to get there.
Yeah, I think it's also possible to have in career transitions while holding the same position. So in my job, I've gone from being an AI researcher to a software developer to a clinical research coordinator to someone who interacts with the FDA to someone who now talks to heads of AI departments at hospitals, and my title hasn't changed. So it's possible by being an entrepreneur or running a small company, you'll be wearing multiple hats all simultaneously and in different occasions. So you get to dabble with a.
Yeah, so another question we would like to ask you is that if you knew you would spend some time of your career as an academic and also in the industry, where would you start? Would you rather start in the industry, or would you rather start as an academic? So would you do a postdoc? Would you consider not doing it? You probably have some thoughts on that.
I certainly have some thoughts and some input, but I don't know if anybody else wants to take it. Otherwise, I can certainly add some stuff. All right, maybe I'll go. My suggestion is you have to be a little bit careful about switching though back and forth between industry and academia, especially very early in life, because they reward different things and they require different things. So if you want to stay in academia, publications are absolutely vital for your progression in academia. And without those, you can't get those positions. So if you do go in industry early as a postdoc, so I did a postdoc, I went after my postdoc and then moved into Stanford after. I was able to publish a little bit in my industry job, but nothing compared to how much probably a peer in an academic postdoc longer than I would have published around the same time. So publications remain quite important. And while in some industries you can publish, and at my company I could have, I still didn't have enough time to really work on my projects and publish at the same time. And and at the same time, there are industries where you cannot publish. That's part of some of the issues. And you don't work on things that are easily publishable because that might not necessarily be as easy of a project, or it's not the types of things you work in industry are quite different than in academia. So as you are doing and thinking about going into one or the other, think a little bit about what's rewarded. And probably the reason why I jumped from industry quite quickly after being in it for 3 years was because I did realize that if I stay a lot longer, I'm going to close the doors towards academia, just because my publication record was kind of going a little down. And I'm just not, compared to other peers the same rank as me, I just won't be competitive. So that's my suggestion there. But again, I think it also depends a lot on what type of industry you go. So GE Global Research was a very established company, which allowed me to publish. Yeah.
I want to add a little bit on top of Dr. Rusu's points on publication and being competitive in terms of publication. So I think one point I want to add is if you want to be competitive in terms of publication to optimize your future career, whether that's going to be academic or that's going to be industry research role, right? So I think academic is actually a really good place to do that. And one perspective or one reason for that is collaboration. So I think this is especially true after I make the transition from being a PhD student to being an academic industry researcher. So in industry, collaborations across institutions are actually harder than when you do so in academic. So think about, like, if you're in Stanford and you want to collaborate with someone from Berkeley, or if you want to collaborate with someone from Microsoft or Amazon or Google or GE, that's actually much, much easier and has a lower barrier than if you want to do so from Amazon. So imagine like Amazon collaborating with Microsoft on some research project. So it's almost impossible. So I wouldn't say that it's definitely impossible, but it's much, much, much harder to do so. So I think that's one perspective to keep in mind if it's something that you really care about.
This is all, again, very helpful feedback. And just before we move on from this question, any other takers? Anyone else want to chime in?
Sure, I can chime in quickly here. I would actually, I try not to think about it as strictly industry versus academia, because even within industry, you can have so many different types of roles. You could be a software engineer and your job is to just ship products every quarter, or you could be working at Google Brain where your job is to keep publishing every quarter. So I try to bring the question back to what sort of skills can you actually develop? And actually one of the most academically useful roles that I had actually came when I was consulting for a company, when I was working in a marketing role too. My job was to sell MR hardware. And the way I would do that was to just go to different academic MR sites and just talk to the researchers and ask them, what are your problems? How are you solving them now? And how will you solve them in the future? Most of the time, I didn't have any background about these problems, but I really learned the skills of trying to understand the problem from the very beginning and try to think about the solution from an end-to-end basis. And as an academic, I think that just translates to grant writing, just being able to tell a very compelling story. And I found that I learned those skills best from an industry position. So I think the answer can vary, and it all comes down to developing a useful skill set.
Can I make a quick comment?
Sure.
Okay, I wasn't sure anybody was hearing me. Akshay mentioned when he was speaking that he would go over his CV every 6 months with his mentors. So I would ask all of the postdocs and engineers in the audience now, do you actually even have a CV yet? Because I would bet not everybody does. And I think it's a very important practical thing to start getting your CV in shape, list everything you do, put it in the right section. And if you want to wind up in academics, for instance, then you have a document with which to work. So very important practical advice suggested by Akshay.
And I would echo that just to say, you know, again, a lot of the feedback here has been very practical, but also I think it's very valuable to us as trainees and to this audience in general to just hear the versatility and diversity of perspectives here. Because again, all of you come from fascinatingly different backgrounds, but I think, you know, all of this is very helpful to hear. And with that, you know, we'd like to shift gears from questions for all of you, maybe to some targeted questions with the time that we have remaining. So I will open up with the first question that is actually directed to Nish. And the question is, what factors influenced your decision to forego pursuing a PhD? And do you think that anything would have been different if you had decided to obtain one versus, you know, going the path that you've gone down now?
Yeah, that's a great question. I think the work that interested me and the problems that I wanted to solve called on pursuing the path that I did. I think trying to figure out how to best streamline collaborations between institutes or figure out what it takes to bring algorithms to widespread adoption, those problems would only be possible in an industry role. We actually thought a lot about how we could stay in academia and still pursue what we wanted to do. But that was analogous to building and maintaining a PAX company within an academic setting. Like there are tasks that are better suited for academia, and there are tasks that are suited for industry. And the problems that I wanted to solve and the tasks that I needed to do fell very strictly within the things that were possible within an industry. So I never had to consciously make a decision whether it was going to be academia versus industry. There was only one option for me. And so I think that also answers the other question that you posed. I can't imagine doing what I'm doing in academia today. It just wouldn't be something that would be academically valuable. It is only something that industry would value right now.
Thank you. So the next question will be directed at Sarah. As you mentioned, you have mentored many students from diverse backgrounds, and including medicine, engineering, and bioinformatics. What projects have you worked on in the past that have translated to your current work?
Yeah, so speaking specifically about projects that I've worked on in the past, translating to my current work. So really my postdoc project really was a building block and stepping stone, I guess, in terms of my independent research program. So I think that for those not really, my PhD or my postdoc work focused on PET-CT for lung cancer and traditional more radiomic analysis. And really this allowed me really to build collaborations both within Stanford and take that and kind of build new directions as part of my own independent research program. So not only still maintaining the collaborations at Stanford, but developing new collaborations at other institutions and kind of using that as preliminary data to get collaborators on board locally. So I think that was really important to be able to show some of our radiologist colleagues here locally in London to see what we've done and get them on board to kind of now let's curate our local database here. Let's build some new research questions and kind of build off from that. So I think that's kind of important in terms of the past work, kind of building it to my future work.
Thank you.
Go ahead.
Go ahead. I had one question for Yuhao as well. So Yuhao, you already touched on it kind of quickly, but you had quite a success in the academic realm when you published a few papers. What made you what was the main thing that made you decide not to stay in academia and do a postdoc and then go to industry?
Yeah, I think first of all, I would like to say that that's an overstatement. So I wouldn't use the word success. I think I was really lucky during my PhD to to be able to work with great mentors like Kurt or some other like great collaborators. So I think that gives me the opportunity to publish. But I would say that there's like so many more people that have been way more successful than I did. So that's the first thing. So in terms of the transition, I think there are mainly two considerations, or mainly two reasons that I want to make that, or maybe three. Let me touch the first two. So the first one is about the work, the scope of the work that I do. So I think in industry, so at the end of my PhD, I really want to get exposed to real applications and real customer, and to build real applications. So I feel like during my PhD, even though I was able to publish a lot, I build new models and get new numbers on things and try to see how that improves medical imaging, for example. I always kind of doesn't have the feeling that I was actually talking to real customers or real users of the algorithm that I actually built, right? There's a lack of that type of feeling in the academic research environment that I was in. So yeah, so I think being in industry gives me that opportunity to actually talk to real customers and see the real feedback on the actual product that I built. So that's the first reason that I want to get exposed to the industry environment. And it's why that is actually very attractive to me by the end of my PhD. The second reason is actually resource. So I think Curtis here, maybe I shouldn't say too much about this, but I always have this feeling during my PhD that actually this is a generic issue nowadays for academic versus industry, is that in academics, especially like if you're working on like machine learning, right? So you need a lot of computational resource to build new models and to make them good. But I think in academia, it's really hard to get a good amount of this computational resource, right? So, but in industry, because it's built on a totally different incentive. We have a lot of resources that can be allocated to research projects like this. So I can access a lot of these resources. So I think that's another factor that has driven my decision, which is a very practical reason. So a third reason that I think I should also mention is that this is I also already mentioned this in some of the previous questions, is that I want to be exposed to more industries. For my PhD, I was mainly solving NLP and especially medical NLP, so applying NLP and imaging to medical problems. But I think being at the current position actually exposed me to more industries like finance or some other industries, and to see the problems in those different industries. So I think that's another reason why I decided to make the transition. Yeah. Hope that answers the question.
It more than answers the question. Thank you. And so the final question I'd like to pose is, I'm actually going to direct this question both to Akshay and to Mirabella. So you get a paired targeted question, which is a slight variation on the question that we had come up with as a panel, because after hearing both of you speak, I think we're very curious as to like the non-traditional paths that you both took. So, Akshay, you did your training here at Stanford and then ultimately stayed on with as a faculty, which is an incredibly impressive accomplishment. And Mirabella, you had the opportunity to work in industry and then come back to academia, which is equally rare and impressive. So I wanted to ask both of you, in taking those paths, what were the biggest challenges that you faced in terms of coming into your academic post? What did you feel was maybe unique about your pathway as a junior faculty relative to other people who maybe took a more traditional path? And also, what were some advantages that you thought emerged from the pathway that you took? So either of you are welcome to respond.
Maybe I can start. I think, and I cannot talk on behalf of the people that decided to hire me. Some of them are here, so I don't know exactly what was in their minds when they make this decision. But I do think that the fact that I had a little bit of industry experience helped, because I have that. I can share that with some of you, the trainees that are in my team and then in the division. So I think there is a perspective. It's clear that in this day and age, not everybody's going to stay in an academic position, and understanding and having the knowledge about how the industry works, I think, is valuable in a professor position as well. I think that's one. Now the challenges is that I think at a certain moment somebody had to trust in me that I will achieve the things that an academic will achieve, although I was coming from industry where I was not coming with an NIH grant, or I was not coming with other things that could have been a plus for an academic position. So I don't know if that was personally my challenge, but I had to prove myself that I can do the things that an academic needs to do while coming from industry, which is write grants, be successful in writing papers again, and all of those. So I think that's kind of how I think. But personally, I think having the experience of the industry has only opened my eyes towards kind of what is possible in industry, what resources are available. I think if you work at AWS, might be a bit different in computational resources compared to if you work at GE. But just, differences, right? They're always going to be there. And so I think I never seen it as a challenge. So personally, I saw it only as an advantage. But yeah, okay.
Yeah, if I had to take a stab at that, I think that's a pretty tough question. But from a challenge perspective, I guess one of the bigger challenges that I probably faced was not having a track record of NIH funding. I had plans of applying to a K-99 grant. I had plans on applying to even a postdoctoral fellowship grant, but just the timing of the faculty positions came up in a time when I hadn't done any of that. So just trying to have a compelling enough case that, as a faculty, you're almost hired to be able to get new grant funding into the university. And the best way you can show that you're capable of doing that is by having shown that you've done that in the past. So I think that was a little bit of a challenge, but something that helped me is, again, my mentor. Even though at Stanford, I didn't have the ability to apply to grants as a PI internally, my PIs were always very supportive of me applying to different funding opportunities that came on campus. 50K grant here, 100K grant over there. Most of them were unsuccessful. But just the fact that I was able to start thinking about that process and starting to write grants, and there were 1 or 2 grants that were successful, and even though they were never in my name as PI, I think my mentors were very kind in writing that in the letters of my recommendation, saying, even though my PI has a grant, Akshay wrote most of it, and Akshay carried out the project. So I think that was a challenge, but I think because of the mentorship structure that existed at Stanford, I was able to work around that. So maybe advice to all your trainees is talk to your PIs about what are potential opportunities that you could get involved with. And then from the unique opportunity standpoint, I think I really benefited from trying to take ownership on the problem entirely. Over my PhD and some of my early postdoctoral work, I was working on some new medical imaging modalities for rapid MR imaging of the knee. So not only was I able to build the new imaging method, I deployed it in the clinic, and I was able to talk to clinicians. I was in the reading rooms, and by the end of the day, I could read maybe 80% of all knee MR scans that came into the hospital. Those are mostly normal, and I think the radiologists get paid for the other 20% that are abnormal. But I think that's something that's unique about academics, where you get to talk to so many different skill sets and then all co-located next to each other. I think that was a really big feather in my cap, that I had the opportunity to be able to work with so many different faculty to own my problem from end to end. So I thought that was pretty helpful for me.
Maybe I can follow up one thing that came to my mind as Akshay was saying these things. One of the things that was a little bit challenging for me actually coming to this position is that I couldn't really bring any of my postdoc projects per se into the new position. One, because I left that job, and two, because I also wanted to, or I needed to establish my own collaborations locally. So I started really from scratch, which I think probably if you look at my record, at least in the first year of my faculty position, I also couldn't hire too many people. So I wouldn't say I struggled, but at least my productivity was not on paper as I would have liked it to be, or at least as it should have been. So I think this transition also can probably hurt me a little bit, as opposed to if I would have come directly from a postdoc. But at the same time, it pushed me towards finding my own collaborators and my own direction, which I think is also important.
Thank you. This is all great advice, and I'm so happy it's all recorded so we can watch it back at some point. And I think it's super useful for all the trainees on the call, and including me, of course. So at this moment, we would like to open the floor for questions. I didn't see that much questions in the chat yet, but you can just raise your hand or unmute yourself and ask the question if you want to. I'm sure there are a ton of questions.
The good news is that there are a lot of very helpful comments in the chat, albeit no questions. So maybe we should save the chat at some point as well, so everyone can have this as a resource. And maybe we'll just take a few moments of pause here to see if the audience has questions, but if not, that just gives Rohir and I the joy of continuing to ask you all more questions. So anything from the audience?
I see a question that Kurt had asked, which setting, I believe we're talking about industry and academia, has the resources that you need to succeed and to solve problems?
Thank you. So that's an excellent question that we definitely missed. So open to anyone on the panel who'd like to start.
I'm happy to give my quick 2 cents, but I'll stop talking very quickly.
And just to clarify, it was a little bit rhetorical in the sense that I felt like that was something that a point that Juha was making, was that you need to ask yourself that question as you're making your career decisions. But I'd be interested to hear what you all have to say about it.
Yeah, I guess I was struck by what Juha was saying, and maybe I'll disagree a little bit to spice up the conversation. I think, at least as we're talking about machine learning, a lot of the algorithms that we're all trying to build can be pretty compute intensive. And we always talk about that, companies can build big models effectively. And I think that's a benefit that the industry has. But I think at the same time, that presents an opportunity for academics also. I know that I'm never going to train GPT-3, and I will never try to do that, or I'll never try to train large models. But I think that allows me to have a little bit more creativity in trying to build new theory, or in trying to build new use case settings where I can evaluate the robustness of these methods. And that's not something that I would be working on if I just had a lot of compute where I might be able to solve bigger problems. So I think just because one side has more compute and another side has less compute, that doesn't preclude opportunities. I think it just provides different problems and different arenas one can exist in. And I actually like working in a small data regime. I feel like that helps me build more robust algorithms, helps me come up with more creative ways of solving problems rather than just throwing a lot of data and compute at it. And obviously, not everyone has to agree with that, but at least that is how I sleep better at night.
Yeah, I think that's a great addition to actually my answer. It's a kind of, I think when I say that, it was mainly like from my personal reason, like why I choose industry. But I think that's a great point, actually. So just think about the example of GPT-3, right? So it's a powerful natural language processing model that's amazingly good at doing like all the benchmark tasks. But I think the problem with that is, if we look at industry has the incentive of building a model that large and being like very, very accurate at specific tasks, but it doesn't have enough incentive to understand why that model works. And also like to try to make that model more robust, probably like try to interpret why the model makes certain decisions. And on the other hand, in an academic environment, because we're doing research purely out of curiosity, I think the incentive is actually very different. So you have the very kind of good environment or the right motivation to delve into problems that sometimes the industry would not have the incentive to do, right? So I think that's a great point to add on top of my answer previously. Yeah, so I totally agree with the point.
Any other comments from our other panelists? If not, I think Stefania has her hand up. So please feel free to
Yes.
unmute and ask your question.
Thank you. So I wanted to say, first of all, thanks for all the great answers for everybody. And I see a common thread we saw here in all the panelist answers is this really moving freely with what your interest is. And I wanted to ask, do you feel we need to dispel the myth a bit about academia being rigid? Because I think very often we have this like people don't feel they have to stick with a certain project or a certain direction, or they feel that it's taboo to ask about this like industry collaborations or connections. And I think this panel has been great at showing otherwise. But yeah, I wanted to ask if you ever felt in your career transitions this part of resistance to flexibility.
Maybe I can try to answer that one. I feel like there is always a little bit of, when you are in academia, sometimes people like PIs and mentors might not necessarily want a trainee to go or might not necessarily want the trainee to go in certain paths. I personally felt that there was a little bit of resistance when I left my postdoc to go to industry, as in I've been told that might not be necessarily the best career move that I have or I will do. And I kind of chose a little bit to ignore some of this. I think I had the same resistance, if you want, also from my PhD to move into a postdoc. That was not the field of my PhD. I kind of choose to ignore them. It is your own path. And while people might have good intentions, it's your path. And my thought process has always been, it's my path, so I'll choose to do whatever I feel like it's the best for it. And kind of a little bit in that direction. I felt like I was a little scared, and maybe goes a little bit that I might burn some bridges by doing that, essentially taking that. And I can say successfully that I have not burned those bridges. I think people respected me for my decisions, although they might have not agreed with them at all times. But
yeah, that's an awesome answer. Thank you.
And I do think coming from industry understands a lot that people move between jobs quite easily. So I think from industry, I didn't get like the same, if you want, resistance, because I think there was no expectation or it was, yeah, it was certainly more common to move across companies.
Can I have a quick comment on that question too? Take my answer with a grain of salt, because I've only really seen this at Stanford, but I actually don't think that the research environment here is rigid at all. I think there's a lot of free flow between multiple different divisions, different departments. And what I would suggest is being able to make use of your trainee status. So if there is a new professor in CS or electrical engineering or genetics that you are interested in their research, but you don't necessarily have that background, feel free to email them and say, hey, I'm a new postdoc at Stanford, or I'm a new PhD student at Stanford. These are some skills that I bring in, but this is what I'm interested in. And try to show that you're eager and willing to learn. And from a value perspective, try to show them that you can also contribute to their research. So I think trainees have a really nice excuse to be able to just reach out and use the new student card. In fact, I use that with different faculty all the time too, and I'm pretty sure that will start wearing off quickly. I email other faculty and say, I'm a new assistant professor on campus. I'd love to chat about your research. So I think people are always willing and open to listen and to consider new ideas. They're busy, admittedly, but I think they'll always try to find the time to try to explore these new bridges, at least at Stanford.
Yeah, thank you for that, actually. And I agree, Stanford is really wonderful at this whole thing. I'm also an example. My PhD is in applied physics, and I found Mirabella's lab. And yeah, it's all very nice to be able to explore this. So yeah, I think the takeaway is take advantage of Stanford. It's a really cool place to explore interests.
Excellent. We're almost on the end of the session, so there's room for one more question. I see Anthony has his hand raised, so feel free to unmute and ask your question.
Thank you. Thank you everyone for the interesting discussion. So two things, two comments kind of to prelude my question. So one, most people here we either have faculty or we have industry, which is interesting. And then the other thing I noted is, as Akshay was commenting, he kind of talked about liking that whole life cycle. So from his research all the way to hanging out with radiologists and understanding how we can implement the technology he developed and whatnot. So I'm curious, and we sometimes see, and maybe more in figureheads often, people who kind of more toe the line, they actually have a foot in academia and in industry. Does anyone have any comments and kind of, or thoughts on the reality of actually being able to do that, or how it may work to actually be a little bit of playing a role in academia and doing the research and maybe actually implementing it in a company or whatever. Yeah, I'll let anyone comment that has any thoughts on that, my vague question. Maybe barriers to it or whatnot.
I'll pick on Nish to answer that because he did that really well.
Yeah, I think I'm fortunate to be in a position where I interact with a lot of academics. We work mostly with academic health centers who build algorithms, and then we do the tasks that they find boring and they do the tasks that we are not best equipped to do. So it's a very nice complementary set of skills. I think it leads to a pretty virtuous cycle of interests and skills and tasks actually, whereby when researchers realize that, hey, there's this mechanism for us to actually see algorithms achieve widespread adoption, then they think about what would lead to most clinical impact and try to build algorithms that are in that light of things. Similarly, when we see what's new in the market in the sense of, okay, there are pre-trained algorithms and foundational models are picking up. So can we actually incorporate them and think about how that might influence the new set of algorithms that might be developed? So I think that industry and academic collaborations are best in my experience when they complement each other and not so much overlap each other. And I've been fortunate to be at that on that front.
Perfect. Well, with that, I believe we've reached the close of our session. In fact, we're a minute past. So I would just like to thank all of our panelists once again for sharing your stories and your immense wisdom with us today. And so maybe a virtual round of applause for for everyone on the panel, and make it real. Everybody unmute and let's give them a nice hearty round of applause. Thank you so much. And thank you to our audience members for your participation. So that closes our panel discussion. Thank you.
Well, thank you, everyone. Thank you, everyone, for joining us today on the virtual format. So tomorrow, we have another exciting day for many of us who are staff, students, faculty who work in IBIIS or AIMI. And we'll have posters, we'll have refreshments, we'll get to walk around, bump ideas amongst ourselves. So hopefully we get to all see you guys tomorrow. So thank you, and we will adjourn.
The room should be spotlighted. Yes, okay.
Okay. Hi, everyone. As I know folks are still coming in, but we'll get started. We have an active day of part 2 of our 2021 IBIIS and AIMI hybrid retreat. And today we are in person. So thank you for being here. So, we'll shortly find Joanna, who's our executive director of the AIMI Center, will share information on resources in the School of Medicine. Then we'll meet some of our AIMI and IBIIS faculty and learn of their exciting research and get acquainted. We'll break at 2:15 with refreshments downstairs out in the courtyard. Then we'll have a poster session also outside. And I'll be the timekeeper to keep us on time. And in the last minute or so, I'll
for some questions. And then at 4 o'clock, we'll have the poster voting and announce poster prize winners, and we'll adjourn at 4:15. And welcome, Joanna.
Thanks, Kristen. Hi, everyone. How are you? Isn't it so nice being together in person? Thanks, Sandy, for joining us. And I'm not sure if anyone else is online, but we are thrilled to be together. Oh, yeah, I see Sandy here. And everyone, welcome. I feel like this is our first AIMI event, and actually AIMI IBIIS event that we're doing in person together. And so this is really exciting. And I wanted to go over a few resources. Some of this may be familiar to you, but I know that there are a few of you who are new or newer. And so I wanted to go over some of the resources that we have available. First, in terms of research, I wanted to talk about our website. And there's a few things that we added to the AIMI website. This is kind of your go-to place for AIMI news events, media clips, links to YouTube videos, our symposium, links to all of the symposium talks. And Jacqueline, who's here, she's the admin for the AIMI Center. Hi. She does an amazing job keeping this website up to date. So in terms of our meeting schedules, are there changes? Is there a journal club coming up? Is there a link to the paper, et cetera? You'll find all of that information on our website. I also wanted to point out office hours, which is under the resources tab. And this is basically where you can sign up for an hour to meet with someone in the team, to meet with faculty. If you just want to chat about an idea, if someone comes to you saying that there's a research project, is there anybody at AIMI who can kind of chat with me about this? Or if there's a project or an idea you'd like to just chat with, then you can submit this really short Google form, and we can coordinate an office hour with people in the School of Engineering, people here in the School of Medicine, et cetera. And so that's a really great resource that's available. There's also a tab in resources called software tools, and that's where you can find links for the annotation tool that we provide through the AIMI Center at MDAI, the STAR cohort discovery tool in the School of Medicine, a montage. There's a number of resources, EPAD, et cetera, and links and some information regarding the software tools are available on the website as well. Many of you know that the AIMI Center has been sharing data sets publicly, so links to all of the data sets, information regarding the data sets, et cetera. We've actually moved that over to a new platform that we've launched with Microsoft, but we do still have information on our website regarding the different data sets that are available and links to the new site as well. Funding opportunities that do come up. Right now, we do have a Google Cloud research credit funding opportunity that is available, and that's for up to $20,000. And that's actually postdocs are eligible to apply for this funding as well. So that's those types of funding opportunities. When we do have open call for proposals, et cetera, you can find details on our website. I also wanted to just highlight our meetings, which I think are a really important resource, but we do have some updates to our meeting schedule for the AIMI Center. On Thursdays, we meet 3 to 4 p.m., but the first Thursdays of every month, we've launched this new trainee meeting where we really wanted to just have this community where trainees can come together and share ideas and thoughts and your projects, your work in progress among other trainees. So that's the first Thursdays. We have our journal clubs, and we actually have really exciting papers lined up for the rest of this year. So that information is on the website. Everyone is welcome to attend the journal club. The authors will be presenting. I think it's really great for the next 2 journal clubs. They're pretty high profile papers, and the senior author and the primary author will both be attending those meetings. So that'll be fun. And then we also, as you know, the third Wednesday is generally at 12 noon. We have the IBIIS AIMI seminar. Third Thursday, we have our general research meeting where we talk about work in progress. That's generally internal work that's in progress, but we also do invite exciting external speakers as well. And then the fourth Thursdays is when we have this live panel discussion. We call it AI Happy Hour. We used to do those on Fridays, but we do those on Thursdays on YouTube. But it's really great in terms of the topics that we're able to cover. And I'd actually like to extend an invitation to everyone here. I know I'm sharing about resources right now, but you are a valuable resource as well. And if there are topics that you'd like to see us cover with panel discussions with external panelists, or if you'd like to help moderate one of these, et cetera, you are a part of our community and would really welcome your ideas regarding that. I wanted to share about the IBIS website as well. And I think everyone here knows Ramsey. As you can wave. So Ramsey is the manager for IBIS, and he also is just fantastic at keeping this website updated. And I really emphasize updated websites because I know many times we come across websites that aren't kept current, but the AIMI and the IBIS websites are really great at keeping current information. So in terms of events, you'll find, of course, information on our annual retreat, speakers, and I really like the recently awarded grants section that they have here. We also have the recent tweets on our website as well, but this is a valuable resource, abstracts for upcoming seminars, and IBIS actually plans the monthly seminars about a year out. So we have most of the speakers planned for 2022 as well. I know the schedule might not be updated for 2022 yet, but they are planned and it will be up soon. So you can see, yeah, what was that? By the end of the year, you'll see all of the speakers, the wonderful speakers that we have lined up for 2022. I also wanted to highlight the radiology research. So this URL is actually radresearch.stanford.edu. But just in terms of our department, there's a calendar that has all of the radiology events, including the various research divisions and clinical grand round talks that they have as well. But just different sections. If you're planning on submitting a fellowship grant, who are the contacts in the department? Of course, you can get a lot of this information from your manager or your PI, but there's a lot of information that's here as well on this website. So I wanted to point that out as a resource. And then also just for postdocs, there's a lot of information. And I was actually informed that a lot of this information, I hope this isn't confusing, but the postdoc advisor said a lot of this information also applies to students. So take a look. There's a lot of great career development information that I think is general that would apply to any trainee. So that's the number one go-to resource for postdocs. I wanted to also just spend a few minutes talking about a well-being resource that I learned about recently through some of the trainees in the AIMI Center, but I wanted to go through real quickly this Be Well program. And it is a well-being program that is actually geared more towards faculty and staff. So I'll go through this actually kind of quickly, but there's just a few components to this program where you can actually get a lot of advice and a lot of support regarding any type of wellness kind of interest of yours. So it's not, so it's very comprehensive actually. It includes being more fit, moving more towards a plant-based diet, etc. Just exercising more. I feel like in terms of COVID, a lot of us had a very sedentary year. So just in terms of that, there are some resources that they provide. There's a lot of resources in terms of just fitness, healthy living, classes, seminars, webinars. There's like a lot of information that is provided through this program. And this is a sample of the types of webinars, et cetera, that are available. And the reason I'm sharing this also for, in terms of postdocs and students, although you're probably not eligible to participate in the incentive aspect, a lot of these classes and webinars are available to you. And I think that they're really, the classes have been very helpful and they're very interesting as well. And this is just a part of the program where you can get incentives for participating. But the part that I thought was also really interesting is that they've started group fitness classes at 1701 Page Mill, which is where the AIMI Center's office is located. And there are discounts for classes, for group fitness classes, fitness passes. And now that they've started group classes at 1701 Page Mill, you don't have to be a Be Well program participant to participate in Stanford Recreation classes, but if you are, you'll get a very nice discount. But I wanted to kind of highlight the group classes because this is open for anyone here. The group classes, if you're part of the School of Medicine, we can help you get access to these classes that are in our building. You're supposed to be working in the Stanford Research Park, which is where the 1701 building is located, and many of you have access to that building. And if you'd like access to the building in terms of the gym, then please talk to me or Ramsey and we can help with that access. But I just wanted to let everyone know that this is available. And in terms of anyone who might be interested in the program, there are a few key dates because this program renews every year and there's a few deadlines that they'd like you to be aware of. That was the main part in terms of the program. I think that was a really quick run through of some of the resources we have through AIMI, IBIIS, our department, and then also just in terms of fitness. And then lastly, I just wanted to also point out that I feel like people are the biggest resources. And so I've introduced Ramsey and Jacqueline. In the AIMI Center, we also have a project manager that many of you may have already met, Stephanie Bogdan. She's not able to attend today. However, she's our project manager with extensive IT information and experience. And so in terms of just getting set up, and if you have questions regarding accessing data and IT, et cetera, there is a fabulous IT team in the School of Medicine, but then there's also a very valuable resource, Stephanie in the AIMI Center, who's very knowledgeable about a lot of the resources and a lot of the tools that are available through the School of Medicine's IT department as well. So she is also a really great resource, and her contact information is on our website as well. And then I think that was the last resource that I wanted to mention, but yeah, 10 minutes. Okay. Any questions or
I just wanted to ask if we can see these slides anywhere or if they can be sent in an email.
Sure, definitely.
Awesome.
Yes, we will email them.
Yeah, great overview. I didn't know about all these things. So thanks a lot for putting them up there.
Wonderful, thank you. Anything else? No?
Okay. Thank you, Joanna. Hello? Okay, great. So that was really lots of great information. I actually actively use some of these websites also, and so and I've been here long, and they're great. So thank you. And I just learned about wellness thing too, so that was also very helpful. So we now get to meet our faculty. So we're gonna first meet Dr. Agipur. Thank you for being here, and we'd love to learn about what you do and your interests and so on. It's not projecting.
There we go. All right.
There you go.
All right. Well, thanks for having me here. I'm a fourth-year assistant professor, and my lab works on a broad range of translational applications of AI and ML with a particular but not exclusive focus on biological modalities. We work on a broad range of clinical problems. Really anything that somebody can convince us is going to have real translational impact in the short term is something that we are happy to work on. And we use a broad range of data sets, including single cell data. With modern technologies, we can now measure millions of cells per patient to really understand their immune system, various omics data sets, wearable devices, electronic health records, and most recently, global level data sets as well. I'll use one of our problems to give you an overview of the type of work that we do. Preterm birth in particular is currently the largest cause of death in children under 5 years of age. And as medicine has advanced and we have figured out how to deal with other issues in babies like sepsis and jaundice and so on, preterm birth has grown to become the largest cause of death, both in low and middle income countries and in countries with advanced healthcare systems. So a large consortium at Stanford has been trying to understand prematurity. We have put together a large group of laboratories that specialize in, for example, cell-free RNA measurements, proteomics, metabolomics, measuring the immune system at a single cell level, microbiome profiling, and measuring cytokines in plasma and serum, to really try to dive deep into the immune system and understand what is causing preterm birth. Putting all of these data sets together, of course, quickly gets complicated, and you start diving into more causal inferences and so on to try to disentangle this biology. But the more interesting part of this story is that for me as a computer scientist, this is the picture that I was seeing, that we're throwing all of these various omics data sets at prematurity, which is defined as a pregnancy that's shorter than 37 weeks. And I couldn't really even remember the number 37. And I couldn't understand why we are going with gestational age to begin with. But I assumed that there must be a good medical reason for this. One day when I was writing a grant, I did a little bit of research on that. And it turns out that gestational age at 37 weeks comes from historic mortality rates from Germany from 40 years ago. That's how we figured this out. And mortality rates themselves come from neonatal morbidities, obviously. And just as I was looking at this, it really looked like an autoencoder, or particularly a neural network with a bottleneck layer. If you're taking all that data, we are forcing it into this narrow definition of gestational age that is supposed to capture all these other morbidities on the other end. When they were doing this, they didn't have computers. They had good reasons to do it this way. We don't have to do it this way anymore. So again, currently in the neonatal intensive care units, that picture on the top is how we think about preterm birth. If you're born before 37 weeks, you're preterm. If you're born before 28 weeks, you're quote unquote extreme preterm. And that's how we make our decisions. But in reality, we have a heterogeneous mix of various neonatal morbidities that we need to tailor our interventions to them specifically. Whether prematurity is affecting your brain has a completely different treatment pathway than when prematurity is affecting your lungs. So an extension of this is that we simply use the EHR data that Stanford has available to us. We link the adult hospital to the children's hospital data and figured out who's parent. That gave us long-term maternal information on these babies. We threw all of these into a fairly standard LSTM with some convolution and so on, all the things that you would expect. Put a bottleneck layer in there, again, just like they did it in the epidemiology days 40 years ago. And we had a predictive model pretty quickly after that. So again, we are taking all the procedures, observations, lab measurements, everything on the left, and the goal is to predict that web of neonatal morbidities on the right in a multitask model. In addition to that, uniquely, we also had access to newborn metabolite screening data from the state of California that we were able to link to our Stanford EHR, and that gave us detailed biological profiling of these neonates as well. So all of these go into a single network, and it turns out we can make pretty good predictions. Black is our AI model, blue is the traditional metric that they're using gestational age, and we're doing pretty well. Not only we're doing pretty well, but also we can predict many of these outcomes before birth. That red column is when birth happens. And for many of them, we can make a prediction before birth even happens, which really provides the caregivers with a lot of opportunities to start interventions early. But that's obviously not all. While our area under the curve for ROC analysis looks good, our precision is not anywhere near something that is going to be implemented in the near future. It's still way better than what they currently have, but I want it to be a lot higher before we are ready for this to be implemented. So the next steps for us are to include other modalities other than the metabolomics information that we had. Other biological modalities need to be integrated into this. And more interestingly, other imaging modalities need to be integrated into our pipeline as well. The first target that we already have exciting preliminary results are from brain ultrasounds, but bowel ultrasound, brain MRI, and other imaging modalities are the next targets that we are very interested in including in our model in the short term. Thank you.
Thank you, Professor. Next, we have Professor Kalsetzer. Could come up. I think we might, right, Ramsey? Mm-hmm.
Thanks. Great, thank you.
Cheers. Hi, everyone. I'm an assistant professor in the Division of Primary Care and Population Health. I work on a variety of things, including causal inference in electronic health record data. Much of my work has been based in low and middle income countries around cardiovascular disease risk factors, other chronic conditions, where I work as well on randomized trials of health services interventions. But I do have some work as well in the deep learning image space, and that's work I want to briefly present to you today, given this forum. And all of these projects they're super collaborative. They're sort of the projects where there's way more ideas and things to do than there are people to do it all. So please reach out if any of this is of interest or you just want to chat, find out more about it. Yeah, these are totally open projects. And I think there are many extensions to these projects as well that we'll be working on over the next few years. So I want to, essentially they fall into two basic categories. One of them is around satellite imagery and other GPS tagged data sources. And that stems from my work in global health, where we're really trying to see if we can revolutionize a little bit the way that global health indicators are currently measured and monitored in low and middle income country settings. Currently, really, it's all based on household surveys, which are very expensive. They only cover a small minority of all communities in a country. So you would, sample maybe 2% or less of all villages and neighborhoods in a country, and then sample 20 households or so in these villages. So you don't really get any geographic granularity around which are the communities that are left behind, that are not doing well. And you only get these data every few years at best. In some countries, we haven't had any of these household surveys for more than 10 years. So the idea is, can we use satellite imagery and other GPS tagged data sources to measure some of these health indicators? And we believe this is quite feasible, given that the remote sensing community has been successful in measuring many modalities, many concepts that are closely related to health. So there's work at Stanford Earth with folk that I work with there, Stefano Amon, Michelle Berg, David Lobel, around predicting household wealth index, so poverty really, but also many other modalities such as surface water quality, infrastructure quality, and all these things, if we put them together, can we predict health, things like child malnutrition indicators or child mortality in low and middle income country settings? That's the basic idea and the motivation of this project. And as I was saying, if you here, this is just a map of when the last household survey, nationally representative household survey, was done in sub-Saharan Africa. And you can see this massive problem that we have there, that many of the data sets we have are really outdated. So you can't really monitor health in real time and monitor health for these international and national goals that are being set. Because, at the moment, many of this tracking is just based on models that extrapolate from past performance. And that's just not good enough, especially given that satellite imagery and other data sources are becoming more and more available. And satellite imagery, the resolution as well, is increasing, year by year. So we think this is a really promising approach to try to fill this data gap. This is a picture, a map that tries to illustrate the fact that in these surveys, only a small minority of all the communities are sampled in a country. And so we've got these massive data holes for a country where we just don't have any data at all. And at best, we can try to interpolate between these different points. But that's also, in many ways, not a terribly convincing approach. So this is the motivation for our work, and we believe it can be done. As I was saying before, this is work that was published in Science by Marshall Berg and the Stanford Earth team, where they have shown that predicting this household wealth index, predicting poverty, which of course is closely related to health, is quite successful, is quite feasible in satellite imagery. So that's work really that we're trying to extend now to the health space. The initial target conditions we're looking at are around child and maternal health, but also adult BMI. The other set of, and this is a project that will be going on. You know, we've got some very promising preliminary data, but it's a project that'll be going on for quite a few years, and we've got many collaborators, and you know, there are many other data types of data that we'd be keen to integrate into this. So please reach out if any of this might be of interest, or you know, you just want to find out more about what we're doing. Then I've got two projects going in the retinal scan space. And here, this is also, again, motivated by some of the work that I've been doing in low and middle income countries. Specifically, we have worked on quite a few randomized trials where we used community health workers to try to screen for diabetes. And the main trouble that we run into is that they are not allowed to work with blood, because you've got these blood products that then can't be discarded properly in the community often. It often requires higher levels of training and higher salaries. So this is something that's been a major hurdle. And the other major hurdle is that a blood glucose is really only of value for screening for diabetes if you are fasted, and there's a lot of problems with making sure that folk are fasted at the time of these measurements. So the idea here is, can we use the retinal scans there, which you can increasingly take via smartphone attachments to smartphone cameras, to screen for diabetes instead of having to use these blood tests, which would be way more feasible, would have lots of advantages, and I think could really revolutionize some of the work that, for example, community health workers are doing in these settings. So, of course, it's already been shown quite successfully that you can predict diabetic retinopathy among those with diabetes. So here now the idea is, can we predict diabetes among the general adult population? And what we're using for this project is the UK Biobank, which is a resource of, it's a large cohort in the UK. I'm sure many of you are familiar with it. But it also has 80,000 retinal scans that we're using, and 15,000 of these folk have diabetes. And sorry, there's also an extension to this project where we are working with people like Steve Ash on the idea to see if we can use retinal scans to predict cardiovascular disease events. And this is it's motivated, sorry, I don't have any slides on this because this is a very fresh idea, but it's motivated by the problem that these clinical risk scores that you're using in clinical practice for cardiovascular disease often require to be accurate cholesterol measurements, which in turn require a lab, and labs are very are often not available in many of these settings, particularly in rural areas. So the idea here is, can we predict cardiovascular disease events better if we instead, we could, so there are different ways of doing this. You could use some of the existing measurements that go into these risk scores and add the deep learning part in retinal scans to it to see how well you're doing. Or even in high income settings, you could see whether the predictions can be further ameliorated if you use all of the different inputs plus retinal scans, deep learning and retinal scans. And there's some work going on by other groups as well in this space. And we want to leverage our UK Biobank data set, which has also 500, it's got over 10 years of follow-up. So we've got enough mortality to look at cardiovascular disease, fatal and non-fatal cardiovascular disease events as outcomes. And that's what we're looking at here for this project. Yes, and also saying I work on a variety of other things, so please reach out if you want to talk about anything. I'm still quite new to Stanford, so always looking to make new collaborations, and also very new to this whole AI in images space. So very keen to make new connections and to find folk who are experts in this area, particularly in the AI front. Thank you.
Thank you, Pascal. That was great. Okay, so Dr. Liao, I think we're ready for you. Thank you.
Thank you. Thank you, Ramsey. Hi, everybody. This is my first in-person talk in over a year, so very excited to be here. I'm a neuro-ophthalmologist at Stanford and the founding director of an orphan disease center called optic disc drusen. It's an optic nerve disease. So I'm excited to tell you about what we do and hope this will spark some new collaborations. I do have one financial disclosure, which is I'm the head of the vision research for the Stanford site for the Verily project baseline. And you'll see one slide on that. So basically, the eyes bring the world to the brain gives us vision, and then that gives us human experience. We're very visual creatures. And so when we have vision issues, it's typically due to a dysfunction, a disconnection, or degeneration of the eye-brain network. And our studies are motivated by looking for biomarkers and being able to assess them in intelligent ways so that we could intervene and detect disease as early as possible, preferably before people lose vision. So here's a case of a 42-year-old woman. She has increased brain pressure. So this is sometimes a life-threatening neuroemergency. And I'm just showing you two examples. So these are the right eye and the left eye on the two rows of the different kind of imaging modalities we routinely do in the Stanford Eye Clinic. The first one is just a color from this photo. So this is what Pascal was referring to in terms of, the UK Biobank data set. It's just a color image, exactly what we see when a clinician looks into the patient's eye. We also do some high resolution optical coherence tomography scans. So the B scan is just a line scan through the optic nerve head where the optic nerve is coming out of the eyeball to take information to the brain. And then the angiography is done without contrast, also at micron resolution. So these are 10 to the -6 resolution, or something like over 100 times higher resolution than an MRI. So we could do these basically routinely. It does not take very long. And patients typically lead to a help in terms of their clinical care, but it's also a seamless way to collect large data set for our AI-based studies. I just want to show you an example of patients with vascular studies. So there's a healthy control on top, diabetes, and then two eyes from the same patient with acute optic nerve and chronic optic nerve stroke. It's to show you the kind of image that we could get. And this is probably the future of diagnosis of diabetic retinopathy, ability to diagnose vascular disease before they actually have some irreversible changes, because we can image them at a capillary level without using any contrast. And through the analysis, again, generating a fantastic data set for this group. Like the first talk, we also are collecting proteomics and metabolomics data, physiome using a smartwatch, looking at the biomarkers in these patients, again, looking at differences that may be able to segregate those who are going to be what we call fast progressors, or those who may develop vision loss versus the ones who won't. Vision loss is often bilateral, and it can be one eye then the other, which give us an opportunity to really look at these patients and determine what the best strategies are going forward using AI type approaches. So I'm going to show a couple of busy slides. This is an outline of our approved study using the Verily project baseline study set. I generalized it, but specifically we're looking at cardiometabolic diseases as the first point. So looking at data set, this is currently about 2,500 study participants monitored over a 5-year period. The second project is looking at ophthalmic imaging, like what's being done for the UK Biobank, except we have slightly more detailed data. And then the last one is incorporation of the smartwatch data. And then lastly, I want to end by mentioning visual motor function. So we look at the world by jumping from one place to another. And this is an example of a control subject just admiring this beautiful painting. We could use this basically to look through the patient's eyes in order to know what they're looking at, what they're paying attention to. And as a collaboration, and this is just a heat map of attention, with others at Stanford, including James Zhou, we've started to analyze our large collection of data, which is done at the eye clinic. We have about over 300 recordings of just these retinal scan. But turn the other way, basically you're looking through the patient's eyes at 500 hertz. And the preliminary data looking at this, we've found that you could actually predict disease based on just 15 seconds of eye tracking. And if you chunk the data, as little as 3 seconds of data is enough for us to predict disease. Obviously, we have to look at a much larger number, but I'm excited that we're on the right track. So with the visual motor studies, basically, we're trying to link the clinic to research and then back to the clinic as a way to develop a paradigm going forward using these AI-based approaches to look at eye-brain diseases. So thank you. Just to summarize, ophthalmic imaging gives us insight to the brain in vivo, as well as the vasculature, which has important implications for disease prediction, not just for eye-brain diseases, but also for human health. And then eye tracking gives us a large data set of time series data that we could then analyze and correlate with a large other large sets of data. Thanks.
Thank you, Joyce. Thank you for sharing us a window into eye as a window into brain and disease. We have Dr. James Zhou, or maybe not. We have Professor Lei Ching. Thank you, Lei, for joining us.
Yeah, well, yeah, this is this is the talk I gave in a different conference, but I didn't really especially prepare for anything. But hey, by the way, my name's Lei Xing. I'm professor of radiation oncology and also electrical engineering. So my lab actually has multiple projects. The first project that we are doing is really trying to understand this complex neural network. Especially we want to understand, what is the feature space data look like, so when you have, layers of abstraction, the information flow. So we really want to really dive into the neural network and then see layer by layer, how the feature changes. So I'll give you some example. What do I mean by that? But so that's basically what. So let's just start with the imaging. So my lab actually work a lot on both imaging and therapy. So on the imaging side, we work on deep learning based like reconstruction for CT, for MRI, for PET, and also on the therapy side for the radiation therapy machine, we do treatment planning, etc. So this is the clinical workflow of radiation oncology. When a patient comes in, we first do a CT or MR scan, and then we can, based on the scan, we can build a patient model, treatment planning, and then we push the treatment plan to the treatment machine, and that typically is a linear accelerator, and then we treat the patient, and then so this whole workflow takes months. Okay, mainly because there's just a lot of inefficiency, a lot of decision-making process need to be done. So on the imaging side, I mentioned that we do image reconstruction. Okay. And also, in particular, we do a sparse image reconstruction. We use deep learning to remove the artifact, motion artifact, metal artifact, you name it, and the scatter, etc. So those are the things that I think deep learning works the best, sparse and also motion artifact. And I don't need to mention this because everybody work on segmentation, right? so that's a basic task. So we also work on that. Treatment planning is very special for radiation oncology. So typically, we have some technician work on the treatment planning. So that's very labor intensive. You talk about the per patient, basically it takes 1 day on average, to get a treatment plan. So with deep learning, we can actually automate the process so that you can really get a treatment plan just with a button click. And of course, the delivery, this process is also a lot of uncertainties. So we try to use deep learning to more accurately target the tumor target, okay, in real time, and also basically increase the robustness and the reliability, accuracy. So last but not least, we do a predictive model. Okay, when patient comes in, most likely, the first question they're gonna ask is how long am I gonna survive, right? After radiation therapy. So what we are doing now is today in the clinic there is a table. So maybe post on the wall of the consult room that the physician gonna look, hey, say based on your stage, based on your, all the data I have, this table tell me. So that's not very accurate. So what we are doing now is really just individualize that process. So, you gave an input of the patient image and also demographic information. We can predict, how long this patient will likely to survive. And what is the toxicity, right? Because chemo or radiation, they all come with a side effect. So what is likelihood for certain level of toxicity? So I'll just give you a quick example. So this is actually a work that done by a student, Shirley Shen. And basically, we try to use prior knowledge or data-driven approach to facilitate the image reconstruction process. So this is a conventional image reconstruction. You take a measurement, and then you go through an analytical model, and then you get a tomographic image. So it's a beautiful process. It's really a Nobel Prize piece of work, but nothing wrong, but except that this whole process is very inefficient in the sense that you need to take a lot of data, right? So in order to get a volumetric image or 4D image, you have to take over about 1,000 patient data, 1,000 projection. Okay, the same thing for MRI. So you have to sample, take a lot of measurement in the case space in order to get a decent image. Okay. So the question here is really, hey, the problem, every patient coming in, they just start from the beginning. So can you start from, let's say, prior patient, right? Because in our clinic, we scan 1,000 and 1,000 patients every day. Can we utilize those data and then to, when a new patient come in, it's not quite new, so you can incorporate those data, and that's what the data-driven is all about. So, so we, so this is, our reconstruction number projection or number measurement. And this is the level of prior knowledge. If you don't have a prior knowledge, and basically this is where you are. And if you include prior knowledge by using deep learning, okay, you train a model, you can actually use very little measurement and yet to get a good image. So this is the work that done by Shirley. You can see that ground truth on the first row, and then this is the one projection CT. So one projection, just think about it. When you're taking a chest X-ray, you are getting a volumetric CT image. And of course, there's two projection, 5. So pretty much you don't really need that many projections to get a reasonable image. And the same thing for, so this is a volumetric image reconstructed using a fluoroscopic image. So you're taking a fluoro and then you get a volumetric image. And think about the indication for biopsy, for all the interventional procedure like cath lab. Sorry. So the same thing for MRI. Actually, so we did the same thing for like a sparse MRI reconstruction in collaboration with John Pauly and all the Shreya, all those MRI people. So we were able to really just get a very little measurement in either in the case space and then to reconstruct the volumetric image. So pretty much, so this is, I mentioned, we can predict patient treatment outcome by using CT, MR, or CT and the isodose distribution, demographic information, and that goes through the network, and then you can predict the toxicity and also the survival. And the same thing for, this is for liver SBRT. It's a stereotactic radio body radiation therapy. It's a type of radiation therapy, but this is for colorectal, outcome prediction. So the survival, how long the patient gonna be survived after, you gave all the lab data, etc. So this is just another highlight. So we working with the urologist, Joe Liao's group, try to use the deep learning to really detect the tumor, the blood tumor, during the cystoscopic image process. And you can see that this laptop is already in our room. So we working on a prospective study. Just in real time, you can identify the bladder tumor and then see how well the model do. Okay, the same thing for colonoscopy. So I'm not, yeah, this is for radiation therapy. It's really in the same spirit. We try to, so the clinical problem here is, we don't see the lung tumor or the pancreatic tumor, even the prostate cancer during the radiation therapy process. So in order to see them, this is the current practice. We have to put some gold marker, surgically implant the gold marker. So using deep learning, we can identify, we can see what you don't see without the gold marker. Okay, so basically this is, and we show that already. So the other thing we are working on really just explainable AI, right? So that's actually it's more on the modeling side. So this is the 3 typical approaches for try to explain your model. So you try to establish relationship between input data and the output prediction. So and also you introduce some perturbation in your input data, right? So that's a second approach. The third approach is really visualization. Try to visualize the feature space data. So I'm not going to talk about this, but let's just go to, so these are the perturbation approach. When you have input data, you have output, you can actually, introduce some perturbation in your input data. For instance, you can block a certain part of the input image and then see what is the influence on the next on the output, right? So visualization, and this is actually what you're gonna see. The feature space data. It's a. I have to say that it is a mess when you're using the current technique, right? Like a t-SNE, PCA, or UMAP. So this is a GoogleNet with the long NH, long 14, the 14 classes, and with basically at a different layer, like a layer 32, 63. I mean, none of the layer actually show you the classes, okay? Even though we know, there are 14 classes. So here, with the technique that we are developing, you can clearly see even from the very early on, you can see the classes, and then basically make a decision. And you can also see how the classes change from layer to layer, and just really monitor the information flow. So the same visualization technique actually can be applied for single cell genetics data. Like this is a single cell RNA sequencing data. So this is the ground truth. This is basically 6 different type of genes. So we were able to really map out so this is the first one, ground truth. The second one is basically using our technique, the technique I just mentioned, visualization. And this is actually the published data. This is how they, you get a gene spatial map. And this is with a marker gene. You can see that using the technique that we can really get a spatial map very accurately, almost perfect. Okay, yeah, I think that's you get a rough picture of what we are doing in our lab. Thank you.
Thank you, Lei. Learned about reconstruction and Drosophila and it's a wide range. Thank you for sharing that. Akshay Chowdhury.
So maybe while Ramsey's pulling up the slides, I just wanted to introduce myself. My name's Akshay. I'm a new assistant professor in IBIIS. I joined almost this time last year. And for this presentation, I wanted to do something slightly different. I just wanted to walk people through what some of the day-to-day projects in my lab look like. And I'm very lucky to be joined by quite a few talented postdoctoral students as well as doctoral students. So I just wanted to be able to highlight all of that work. And as you'll see throughout this presentation, a fundamental theme for all the research that I do is trying to utilize a lot of machine learning-based methods in medical imaging, but we're really trying to go beyond this notion of supervised learning, where we require large labeled data sets. So I really want to be able to do more, but using less labeled data. And as an overall premise for a lot of the glue that binds my different research projects is I want to be able to come up with high-value healthcare systems. And I define value in healthcare pretty easily. It's basically the outcomes that a patient can have for any given costs. So if we want any sort of high-value healthcare, what we would ideally like is something that has better outcomes and something that has low cost. So these are the 2 principles that guide a lot of the research projects that are going on in my group. So let's start first with MR. And Lei's presentation laid a good foundation for this. MRI is an expensive modality, so there's a large incentive to be able to speed up a lot of the acquisitions that we have.
So here in this case, we see 8x undersampled MRI data, which means that we're scanning 8 times faster. And if we just use our nominal reconstruction methods, we see pretty bad quality zero field images. And we're working on some methods in the middle that you can see with the 3D DL Recon, where we actually can introduce physics into our deep learning-based models and our knowledge of how the MR scanner actually works to be able to come up with high-quality reference images. So this is what we're starting off with, and this is purely in a supervised setting. But then can we actually make this problem harder when we don't have supervised training data? So that's where we're working on some semi-supervised machine learning methods. Imagine we have a case where we have one fully sampled data set that we can use for supervised learning, and we have a bunch of clinical scans where we only have the undersampled data. So can we still utilize the signals that we can get from these fast undersampled images to build useful networks? And what we've actually done is we're using augmentations inspired by advances in contrastive learning to actually change the way our networks are learning. And here, it's a little bit of a busy slide, I apologize. But on the right side of the screen, you'll see our noise to recon method. Those are image reconstructions that are generated using only one fully sampled data set. And if you compare that with the second column image, where we're comparing to 14 fully sampled images, we get nearly identical image quality. And I think this is because of that way we're introducing augmentations throughout our network itself. So I think this lays a lot of new foundations for better utilizing data efficiently for inverse problems in medical imaging. Next, another challenge that we face is how do we evaluate image quality? The conventional metrics that we use in computer vision, like peak signal to noise ratio or structural similarity, they don't necessarily correspond with human perceived image quality. So we're working on a project where we can use self-supervised systems that are domain specific to build better metrics of image quality without requiring any sort of labels. And here in the bottom row of images, we can see how our new self-supervised learning methods compare with traditional image quality metrics. And here we're just plotting structural similarity. And we can see that if we look at different network representations, we actually see a lower correspondence with structural similarity. So what this shows is that we have the flexibility to be able to choose both low-level image features to enforce image quality. So this is what we're seeing in the early parts of the network. And as we go deeper, we can actually get higher order information statistics about the images that we're building. So hopefully, this can help generate better metrics for evaluating image quality. So now all of these methods can be helpful for generating images, but once you generate images, they're only as useful as the insights you can derive from them. So that's why there's a lot of focus on trying to come up with data efficient segmentation techniques too. So this is a method for using self-supervision on unlabeled data. The premise is pretty simple. We take some reference image and we can impart some arbitrary corruptions. In this case, we're just blanking out different parts of this image, and we train a network simply to fill in those images because we always have the original images that we start off with. And once we generate that model that has learned to fill in those corrupted images, we can use that as a starting point to fine-tune our few-shot segmentation process. I think what we're learning here is that this premise is pretty simple, but the devil really is in the details. Once we have this initial pre-trained network, actually fine-tuning it for the task of interest can actually have a lot of different parameters, such as, do we only use the encoder? Do we use a full network? How do we switch our loss functions? What are some considerations about learning rate? So I think there's a lot of interesting and practical lessons that we're learning, and hopefully we'll be able to open source all this work quite soon. Next, we want to be able to create data sets that can allow for end-to-end analysis and utility of some of the methods that we build. So if we start off with some image reconstruction methods, we don't want to just end at building an image. We want to be able to use these images in a realistic clinical setting. So thanks to the Stanford AIMI Center, we're very close to releasing a data set fully publicly where we have fully sampled case-based data for these MR scans. We have the high-quality images. And for all those images, we have segmentation labels, and we have detection pixel-level bounding boxes too. And as far as I know, this is the first data set of its kind, so I'm very excited to see where we can go with this. And then next, as you've probably noticed, most of these methods that I showed you, they're relating to knee MRI scans. And maybe that's because I'm biased. I like playing sports, and because of that,
I get injured, my friends get injured. So I have a real interest in trying to determine injury and how people recover from injury. And for that, I really want to be able to combine structural insights with functional insights about how joints are performing. So that's where I use a very broad definition of what medical imaging is. If we simply take videos of people in motion, we can build deep learning based algorithms that can actually estimate the kinematics of subjects in motion. And once we have these kinematics, we can actually build customized musculoskeletal simulations of how those patients or how those athletes are performing. And if we can go from this video to this musculoskeletal simulation model, now we can perform things like computational surgery, we can have computational interventions. So what if I want to jump 2 inches higher, what muscles should I work out? And I think these models can help us answer questions like that. Next, I wanted to switch modalities a little bit. And a lot of the initial deep learning methods that I was working on focused on MRI, but recently I've been more interested in trying to come up with population level insights too, using this notion of opportunistic CT scans. And a few speakers earlier brought up, the large burden of cardiovascular disease. And what we've noticed is if we just take clinical abdominal CT scans, we can do some pre-processing and analysis with it. But if we take those images, combine that with the patient's medical record, and we can optionally combine that with the patient's radiology report too, we can actually predict future disease incidence. And we've shown that this future disease incidence for ischemic heart disease, we can do that better than traditional clinical risk assessments. And we have a lot of projects ongoing right now where we can do that with not just with heart disease, but also looking at hypertension, chronic kidney disorder, and osteoporosis, all using scans, which are sitting in our packs already, and with electronic medical records that we have access to. So really trying to perform high value care using data we've already acquired. And I think this really jumps into this notion of being able to personalize a lot of the methods that we use, not just for image analysis once you've generated the images, but in being able to generate those images in the first place. A big challenge is when you go to your physician complaining of, say, stomach pain, and you're assigned some imaging, trying to figure out what is the appropriate imaging protocol that you should receive can have a lot of errors too. So we're building some machine learning models that take into account the patient's medical record, and we're building some models that take into account radiology-specific NLP to make sure that the imaging that a patient receives is optimized for their clinical indications and the symptoms, so that the imaging test that we perform is correct the first time around without requiring any sort of patient recall. In addition to that, there's a lot of excitement in the group to be able to understand why networks make prediction. So similar to what Lei had mentioned in his previous work. And one perspective that we're taking on this is this notion of counterfactual development. Say I have a model that's predicting cardiomegaly, which is an enlargement of the heart. We can build these counterfactual models that can change the risk of that cardiomegaly on a per patient basis. And one intuitively would imagine that if the risk of an enlarged heart is changing, the image level changes that one would see should be in the heart. So this model can actually try to visualize what are some of the features that the model learns and how those features learn based on changing input functions without requiring any sort of access to any underlying training data. And we've recently been able to do this at a higher resolution too, using StyleGAN-based autoencoders. And then lastly, another really interesting project is, can we actually use medical specific insights to build self-supervision models? And this is some work that Rahir will be presenting in this poster session later. But if we have Checkspert, if we have that data set, and if we have associated metadata with that too, such as age, can we actually pre-train models just to predict that age, and then use those pre-trained models to do your downstream classification? And again, the idea sounds pretty intuitive, but the devil is really in the details. So coming up with a scheduler of how we can actually use these images, we actually end up coming up with different cropping mechanisms to go from a fine to a coarse grain image representation. Now, initially, our crops are very small. And then as the model is learning, those crops become larger and larger. I think there's a lot of data that we're sitting on already that we're not able to utilize.
So our goal is to be able to use as much data that we have to build the best possible models. And all this work is possible only due to all the awesome students and staff that work with me. And I'm always happy to chat more about projects. Feel free to Slack me, email me, and I'd be happy to chat over a cup of coffee. Thank you.
Thank you, Akshay. Greg, I think we have you coming up, and thank you for sharing how machine learning can add value, right, to medical care. Greg, we have you up. Thanks for. Oh, it's up in the screen.
The first thing I'll say is I'm nowhere near as organized as all the other people in this talk. And I just want to try to outline a little bit about what we do. And, the only real way to learn more is to just learn more and talk. So I want to talk a little bit about our group called the Center for Advanced Functional Neuroimaging, which I run along with Mike Mosley. And I have a mission statement. And right under my mission statement, there's a picture of Sandy, but on my screen at least, which is not a bad mission. So one of the things we believe is that there's much more information in imaging studies that we utilize. Current neuroimaging study, I'm a neuroradiologist, probably has about 2,000 images. Maybe you guys have more over at Packard, but so we can only really look at them for a very minimal amount of time if we're going to see more than a couple patients a day. So I think that this is a problem that we have to address, and I think this is one thing that AI can really help with. The other thing that I believe is that imaging is much too expensive. And because it's expensive, we have to ration its care. And because we ration its care, it means that it's inequitable. So that the kind of care that I get here at Stanford is going to be very different than somebody gets in a rural location or a developing country. So I think that AI can be used to improve this major problem of imaging. I'm a radiologist and I need help. There are a lot of demands on your time, and there are a lot of very difficult tasks, but there are also a lot of tedious tasks that we do. And if you ask any radiologist, they'll probably come up with a very quick list of things that they think that an average 10-year-old can probably do quite well. And I think these are great targets for AI type algorithms. I'll talk about some of the things we're working on in that area. And then my long statement, which is that, what our group really is interested in doing is combining imaging and clinical information to not only better diagnose disease at the time, but I'm really focused and interested on the idea of predicting the future on an individual basis. And I think this is something that should be our goal over time. It hasn't been historically, but I think we're really at the cusp of the chance to do this in a really great way. So what are the projects in our group? I just want to talk about a couple of them. I'm very interested in image transformations. So Lei talked a little bit about this. Akshay's work to some extent includes this, but it's basically taking an image and predicting another image. You're taking an image that might be acquired faster, at lower radiation dose, without contrast, and trying to get as much information out of it as possible and to put it into a form that radiologists are used to looking at. So for example, if I can create a PET scan from the information in an MRI, that's great because now all the places in the world without a PET scanner now have access to this kind of information. And radiologists are trained to understand PET scans. They may not be trained to understand changes, very subtle changes on MRI. I'm also very interested, as I mentioned, in predicting the future. We have a lot of interest in longitudinal imaging. A lot of the job of radiologists is tracking people over time. And so, we've developed a lot of data. And there are fast changes and there are slow changes. So fast changes include things like acute stroke, where you have a stroke, you're normal 1 minute, the next minute you're not. And in a couple of days, your brain's going to look very, very different. There are other things that are much more slow, like dementia, which happens over decades. So, can we predict this in advance? And can we predict not only, what the image looks like, but maybe some important biomarkers, such as how much amyloid is accumulating in your brain? And, the goal of any longitudinal work, I think, is very exciting because, this may enable you to not only identify and treat the patient in front of you, but potentially identify patients who are going to be ideal candidates for clinical trials. So for example, in Alzheimer's disease, if you want to study how well a drug works, you have a choice of who to put into your study. And if the people that you put into your study are all very, very slow progressors, that means you have to have a very, very long trial to figure out the answer. So can we identify patients who are going to progress very quickly and potentially enroll them, shorten the length, and shorten the cost of clinical trials? So those are kind of the interests of our group. And if you're interested, what I would encourage you to do is just drop in on one of our lab meetings. We meet Thursdays at 2 p.m. My email is on the bottom right. And just shoot me an email and I can send you the Zoom. I think that's the best way to learn about a new group anyway. So that's it. Thank you.
Caffeine. Did you guys get that? Caffeine. Thank you, Greg. That was great. Kurt, Dr. Langlotz. Now that we're all caffeinated.
It's great to be here with all of you today. I see we're running a little over, so I'll be quick. My name is Kurt Langlotz, director of the AIMI Center. I do have my own lab. I wanted to start with this. This is the first paper I ever wrote in 1982. And you can see here that I was a little tentative about my writing. I called it a draft, preliminary draft, first preliminary draft. And my advisor had a sense of humor. He sent it back to me with this initial first preliminary draft. And this is what it looked like when it came back to me. So I like to think about this because it just reminds me of kind of where I came from. And I'm very grateful and really inspired by everyone at the AIMI Center, all of you and all the work that you do. And I'm just delighted to be able to collaborate with all of you. We have now over 120 affiliated faculty in the AIMI Center. I am especially pleased to be able to work with a whole variety of graduate students and postdocs. And sometimes I'm the primary advisor, sometimes I'm the secondary advisor. I really like to collaborate across disciplines. So many of these projects are co-advised by Akshay, who you just heard from, Chris Ray, Andrew Ng. I'm forgetting so many. Let's see, Pranav, Andrew, Chris Manning, James O. So working with Christian Bluthkin, who's not here today, but on classification of interstitial lung disease, working with Rohir Vandersluis on a couple of things, collaborating with Akshay on analysis of digital breast tomography and general methods to improve classification accuracy that you just heard about, and you'll hear about it in a poster. Natural language processing of radiology reports with Pierre, who's here. You'll hear about that in a poster, including detection of COVID-19 and de-identification, which is an important problem. RADgraph, which is something I've been wanting to do for a long time, and that is extracting knowledge graphs from radiology reports so that we can get exact information about which findings occur where and use those as labels and for other purposes. Yuhao Zhang, who's a BMI graduate student who just graduated, but did a lot of work on summarization and generating accurate summaries of radiology reports. Sarah Hooper, who's here, working with Chris Ray and I co-advise her as well on improving segmentation using weak supervision. And then Kevin Wu is a second-year BMI student, hasn't really selected on a topic yet, but we're talking a lot about optimizing translation of image analysis models and measures to optimize training. And then I also work on some ethics policy and other national initiatives. And so you're going to hear a lot about a lot of this in the poster session, so I don't want to duplicate that, but I'll just tell you about some of the things that you may not hear about in the poster session. And this is the knowledge graph extraction. So we built one of these large language models to extract both entities and relations from radiology reports. Built a very simple language model that we could train annotators to reproduce. That's something that I think has been missing. The models have been, the information models have been either way too complex or so simple that they don't capture the true semantics. So this is kind of a good middle ground, and we did get some very high accuracy in extracting these knowledge graphs from chest X-ray reports, and we're looking at how well that generalizes to other areas of imaging. Also, David Larson is the primary author of this work and did a lot of the great writing on the ethics of data sharing, particularly image data sharing. I'm super proud of this work. It's really about using that health data should be considered a public good once it's been used for clinical care, and how that means we ought to treat our health data. In fact, we're working on a grant now to the Gordon and Betty Moore Foundation that's very interested in diagnostic excellence about the implications of that. So how do you get an organization ready to share its data so we can maximize data sharing? What are the attributes of a data set itself that make it AI ready and useful to other researchers? And then just a catalog of all the data sets that are out there, and applying that sort of rubric of ranking in terms of quality. We did some work that was published. This is with a junior faculty member in bioengineering, Amit Kaushal, and also Russ Altman. We did some work on where is the data coming from today for machine learning on imaging. And if you look at diagnostic imaging, clinical machine learning cohorts, where do the data come from? They come from pretty much 3 states and not much else. So there's not a lot of diversity there. And in part in response to that, that was published in JAMA earlier last year, I got involved in a project called MIDRIC. This was in response to COVID-19 and brought together the 3 major radiology organizations, RSNA, ACR, and AAPM, which is the physicists organization, to create a national repository of COVID images. So this repository ingests images through the RSNA and ACR, makes them available publicly. It will make available about 60,000 images in the next, by the end of the next month, and it'll continue to grow from there. And we expect that this infrastructure that's being built could also be used for other diseases. There also are 12 research projects, some of which were funded. So Sandy, Akshay, others at Stanford are funded, and others around the country to actually conduct research on the data that we're pulling together. So that's an important kind of counterpoint, bring diversity by aggregating data across multiple sites across the country and across the world to study a given disease. Here you see the kind of diversity mix of the data there. So I'll stop there. I know we're running up against time. I am, again, super delighted and gratified to be working with all of you, and I am happy to meet with anyone at any time if you have any questions about research or career or otherwise. So thanks for being here.
Thank you, Kurt.